Azure Service Bus Unveiled, a practical guide to resilient cloud messaging. Chapter 1, the why and what of asynchronous messaging. Imagine a bustling restaurant kitchen, a central hub orchestrating a symphony of culinary creation. Orders flow in, ingredients are prepared, dishes are cooked, and finally served. Now, picture an alternative. Every customer who places an order must wait at the counter for their entire meal to be prepared, from ingredient retrieval to final plating, before they can even sit down. The kitchen staff would be overwhelmed, customers would be backed up at the order counter, and the entire operation would grind to a halt. This simple analogy highlights a fundamental challenge in the world of software development, particularly as systems grow in complexity and scale. Traditional, direct communication between disparate parts of a software system can often act like that inefficient restaurant counter, leading to bottlenecks, fragility, and a poor user experience. This is where asynchronous messaging patterns, and specifically highly capable tools like Azure Service Bus, step in to transform the entire operation. The challenges of synchronous systems. For decades, the dominant paradigm for software communication involved direct, synchronous calls. When one software component, let's call it Service A, needed something from Service B, it would make a direct call, perhaps an API request or a function invocation, then pause and wait for Service B to respond. Only then could Service A continue its work. While seemingly straightforward, this approach presents several significant drawbacks in modern distributed cloud environments. Tight coupling. Services become intricately linked. Service A explicitly knows about Service B, its location, and its interface. If Service B changes, moves, or becomes unavailable, Service A immediately feels the impact. This interdependency makes it hard to evolve services independently, update them without affecting others, or even deploy new versions without carefully coordinated downtime. It's like having every chef in the restaurant directly wired to a specific diner. If a diner leaves, that chef becomes idle, and if they change their order mid-meal, chaos ensues. Cascading failures. If Service B experiences an issue, a slowdown, a crash, or a network problem, Service A will be stuck waiting. This delay can lead to Service A timing out, consuming excessive resources, or even crashing itself. This domino effect can quickly bring down an entire system, even if the initial failure was isolated. Scalability bottlenecks. In a synchronous world, Service A can only process new requests as fast as Service B can respond. If Service B is under heavy load or inherently slow, perhaps it's performing a complex, long-running computation, it becomes a bottleneck for all services calling it. Scaling Service A might not improve overall throughput if Service B remains the choke point. Poor responsiveness. For user-facing applications, synchronous operations often mean the user has to wait for a complex background process to complete before receiving a response. This leads to frustratingly long loading spinners or unresponsive interfaces, detrimental to user experience. These issues are further amplified in the era of microservices architecture, where applications are deliberately broken down into many smaller, independent services. While microservices offer incredible benefits in terms of agility and separate development, they magnify the communication challenge, turning a few direct connections into a complex web of interactions that can be difficult to manage and debug. The promise of asynchronous communication. Asynchronous communication offers a powerful antidote to the synchronous dilemmas. Instead of making direct, blocking calls, services communicate by sending messages to an intermediary. This intermediary then reliably delivers the messages to the intended recipient, often at a later time, without the sender having to wait. Let's revisit our restaurant analogy. Instead of directly serving diners from the counter, orders are printed out and placed on a queue in the kitchen. Chefs pick up orders from the queue as they become available and prepare them. Once a dish is ready, it's placed on another queue for the waitstaff to deliver. In this model, the order taker doesn't wait for the meal to be cooked, the chefs don't wait for the diner to be ready, and the waitstaff work independently of the kitchen. This paradigm shift yields tremendous benefits for distributed systems. Decoupling, the most significant advantage. The sender and receiver no longer need direct knowledge of each other. They only need to agree on the message format and the common message channel. This allows services to evolve independently, be deployed at different times, and even be implemented using different technologies. Service A sends a message and continues its work. It doesn't care who processes the message or when. Resilience and reliability. Messages are typically persisted by the intermediary until they are successfully processed. If a receiver is temporarily down, the messages wait. When the receiver comes back online, it picks up where it left off, processing the backlog. This makes systems much more tolerant to transient failures and network glitches. Messages are rarely lost, ensuring critical operations eventually complete. Scalability. Asynchronous communication naturally promotes scalable architectures. If demand for a particular task increases, multiple independent consumers can pick messages from the same intermediary queue, distributing the load and allowing the system to scale out horizontally. Similarly, producers can send messages at their own pace without being hindered by the processing speed of consumers, enabling burstable traffic handling. This is often referred to as load leveling. Improved responsiveness. A user-facing application can immediately acknowledge a request, e.g., "Your order has been placed," and then delegate the long-running processing to an asynchronous message. This provides an instant response to the user, enhancing their experience, while the background work proceeds without blocking the user interface. Auditability and observability. The intermediary can serve as a point of truth for tracing messages, understanding system flow, and even replaying events for debugging or analysis. What is a message broker? At the heart of asynchronous messaging sits the message broker. A message broker is an intermediary software component that facilitates communication between applications by receiving, storing, and forwarding messages. It acts as a central hub, managing message queues and ensuring reliable delivery even if the sender or receiver is offline. Think of a message broker like a post office. When you send a letter, you don't care how it gets to its destination, only that it gets there reliably. The post office handles all the complexities of sorting, transporting, and delivering the letter. Similarly, a message broker manages the complexities of asynchronous communication, queuing, holding messages temporarily until a receiver is ready to process them. Routing. Directing messages to the correct destination, which can be a specific service or multiple services. Persistence. Ensuring messages are not lost even if the broker restarts. Delivery guarantees. Implementing mechanisms to ensure messages are delivered at least once, or even exactly once, for critical operations. Message brokers are indispensable for building loosely coupled, resilient, and scalable distributed architectures, forming the backbone of modern cloud-native applications. Introducing Azure Service Bus. Within the vast landscape of Microsoft Azure's cloud services, Azure Service Bus stands out as Microsoft's fully managed, enterprise-grade message broker. Designed to handle the critical, reliable messaging needs of complex applications, Service Bus provides a robust platform for decoupling applications and services, enabling them to communicate asynchronously. Why choose Azure Service Bus? As a managed service, it removes the operational overhead of setting up, maintaining, and scaling message brokers yourself. Microsoft handles the infrastructure, patching, backups, and high availability, allowing you to focus on your application logic rather than plumbing. At its core, Azure Service Bus offers two primary messaging paradigms. Queues. These are used for point-to-point communication. A single sender sends messages to a queue, and a single receiver processes those messages. Messages are typically consumed in a competitive manner by multiple instances of the same receiver, allowing for horizontal scale-out of processing. Think of it as a single line of customers waiting for the next available cashier. Topics and subscriptions. These enable the publish-subscribe pattern. A sender-publisher sends messages to a topic. Multiple receivers, subscribers, can then create subscriptions to that topic. Each subscription effectively gets its own copy of the messages sent to the topic, allowing a single message to be simultaneously consumed by multiple, independent services. This is like a news agency publishing headlines to a central wire and various newspapers, subscribers, each receiving their own feed to print. Beyond these fundamental constructs, Service Bus provides a rich set of advanced features crucial for enterprise scenarios, including message sessions, ensuring ordered delivery and stateful processing of related messages, transactions, grouping multiple send and receive operations into an atomic unit, dead letter queues, a dedicated holding area for messages that cannot be processed, aiding in troubleshooting and error recovery, duplicate detection, preventing multiple processing of the same message, message filtering, allowing subscribers to selectively receive messages based on defined rules, scheduled messages, sending messages for future delivery. Azure Service Bus typically forms the communication backbone for microservices architectures, command and event processing in domain-driven design, long-running business workflows like order fulfillment, and bridging on-premises systems with cloud applications. It's the go-to service for reliable, high-value message delivery. Distinguishing other Azure messaging services, Azure offers a suite of messaging and eventing services, and while they might seem similar at first glance, they are designed for distinct use cases. Confusion often arises, but understanding their primary purpose clarifies when to use each. Azure Storage Queues, purpose, simple, high-volume queuing. Best for scenarios where you need to queue millions of messages at low cost, and the advanced features of Service Bus, like topics, complex filtering, transactions, or sophisticated delivery guarantees, are not required. Think of basic task queues or logging. Key difference: storage queues are built on Azure Storage, offering extreme scale and low cost per message, but they lack the enterprise features and rich API of Service Bus. They only support queues, not topics. Azure Event Hubs, purpose, high-throughput event ingestion and stream processing. Best for scenarios involving millions of events per second, such as telemetry from IoT devices, clickstream analytics, or capturing large volumes of log data. It's designed for many producers to many consumers for real-time data streaming and processing. Key difference: Event Hubs is an event ingester and stream processing platform, not a traditional message broker for discrete, command-driven operations. Messages are typically immutable facts or events that happened, which are consumed by multiple applications for analytical purposes. Once an event is read from Event Hubs, it's not removed, allowing multiple consumers to read the same stream. Azure Event Grid, purpose, reactive, event-driven architectures. Best for responding to events that originate from other Azure services, like a new file being uploaded to blob storage or a database change, or from custom applications. It's a routing service that pushes events to various handlers, Azure Functions, Logic Apps, webhooks. Key difference: Event Grid excels at dispatching notifications about events. It's not a message queue or a stream processor. It ensures events are delivered to handlers, but doesn't persist messages for long periods or provide transactional capabilities. Think of it as a super-efficient internal notification system. To summarize, while all these services deal with data flowing between applications, they operate at different levels and serve different primary purposes. Azure Storage Queues, simple, cost-effective queuing. Azure Event Hubs, high-volume event streaming and data ingestion. Azure Event Grid, reactive, event-driven routing. Azure Service Bus, reliable, enterprise-grade message brokering with advanced features for complex asynchronous operations, commands, long-running workflows, robust transactions. In this book, our focus will be squarely on Azure Service Bus. It is the workhorse for building enterprise-grade, reliable, and decoupled asynchronous systems in Azure. Conclusion: as you embark on your journey through the capabilities of Azure Service Bus, remember the why behind asynchronous messaging. It's not just a technical alternative, it's a fundamental shift in how we design and build distributed systems. By adopting asynchronous patterns with a robust message broker like Service Bus, you unlock the potential for truly decoupled, resilient, and scalable applications that can withstand the rigors of the cloud environment. In the next chapter, we will roll up our sleeves and begin our hands-on exploration. You'll learn how to set up your first Azure Service Bus namespace, create queues, and send and receive your very first messages, laying the practical foundation for the advanced concepts to come. Chapter 2: Getting Started with Azure Service Bus. Having understood why asynchronous messaging is so crucial for modern distributed systems, it's time to take our first practical steps. This chapter will guide you through the initial setup of Azure Service Bus, exploring its different pricing tiers, and then walk you through the simplest yet most fundamental operations: sending a message to a queue and receiving it. By the end of this chapter, you'll have your first functional message-driven application running in Azure. Setting up your Azure Service Bus namespace. Before you can send or receive any messages, you need a home for your Service Bus entities. In Azure, this home is called a namespace. A Service Bus namespace is a container that provides a unique scoping for all your messaging components, such as queues and topics. It acts as a fully qualified domain name, forming the base address for your messaging operations. For instance, if you create a namespace called myCompanyMessaging, your queues might be addressed at mycompany-messaging.servicebus.windows.net/myqueue. Let's walk through the steps to create one using the Azure portal. Log in to the Azure portal, open your web browser and navigate to portal.azure.com. Sign in with your Azure account credentials. Search for Service Bus. In the search bar at the top of the portal, type Service Bus and select Service Bus from the services list that appears. Create a new Service Bus. On the Service Bus blade, click the +Create button. This will open the Create Namespace form. Configure namespace basics. Subscription. Choose the Azure subscription you wish to use. Resource group. Select an existing resource group or create a new one. A resource group is a logical container for Azure resources that you want to manage as a unit. For learning purposes, creating a new one like Service Bus Samples RG is a good practice. Namespace name. This must be globally unique. Choose a name that reflects its purpose. For example, your initials book SB namespace 123. Location. Select the Azure region where you want to deploy your Service Bus. Choose a region close to you or your target users for lower latency. Pricing tier. This is a critical choice and impacts cost and available features. We'll dive into this next. Once you fill in these details, click Review + Create, and then Create. Azure will provision your Service Bus namespace, which typically takes a few minutes. Understanding Service Bus pricing tiers. The pricing tier you select for your Service Bus namespace significantly impacts its capabilities, performance, and cost. Service Bus offers 3 main tiers: Basic, Standard, and Premium. The Basic tier. Cost model, billed per operation, e.g. messages sent, messages received. Features, only supports queues. Limitations, does not support topics, sessions, transactions, or advanced features like message deferral or duplicate detection. It has lower throughput capabilities compared to Standard and Premium. Use cases, ideal for simple, low-volume development and testing scenarios where only basic queuing functionality is needed, and cost is the primary concern. Not recommended for production workloads due to limitations in features and throttling. The Standard tier. Cost model, billed hourly, structured around brokered connections and operations. It also has a daily messaging unit charge based on usage. Features, supports queues and topics. Includes essential enterprise features like sessions, transactions, duplicate detection, message deferral, and scheduled messages. Limitations. Shared capacity, meaning your namespace might contend with other users on the same underlying infrastructure. Throughput can vary. Use cases. This is the most commonly used tier for development, testing, and many production workloads that require a balance of features, reliability, and cost-effectiveness. It offers the core capabilities needed for robust asynchronous systems. For practical learning and most scenarios in this book, the Standard tier is the recommended starting point. The Premium tier. Cost model, billed hourly based on messaging units, MUs. Each MU provides dedicated capacity, CPU, memory, storage, offering predictable throughput and extremely low latency. Features. Includes all features of the Standard tier, plus dedicated resources, no noisy neighbor issues, your resources are isolated. High throughput and low latency, predictable performance even under heavy loads. Virtual network, VNet, integration. Allows you to isolate your service bus in your own Azure private network for enhanced security. Private endpoints. further enhances security by allowing private access to your service bus from within your VNet. Geo-disaster recovery provides automatic failover to another Azure region. Larger message sizes supports larger message payloads. Use cases: critical production applications requiring the highest throughput, lowest latency, guaranteed performance, and advanced networking security features. Scenarios like high-volume financial transactions, real-time analytics, or applications with strict compliance requirements often opt for premium. Recommendation: for the exercises and examples in this book, the standard tier provides the full suite of features we'll be exploring without the higher cost of the premium tier. If you've just created a basic tier namespace, you can easily upgrade it to standard, though not downgrade from standard to basic. Connecting to your service bus namespace. Once your namespace is provisioned, you'll need a way for your applications to connect to it. Azure Service Bus uses a concept called Shared Access Signatures, SAS, for authentication and authorization. A connection string is essentially a convenient packaging of the necessary information, namespace address, SAS key name, and SAS key value, required for an application to establish a connection. To get your connections string from the Azure portal, navigate to your Service Bus namespace in the portal. In the left-hand menu, under Settings, click on Shared Access Policies. You'll see a list of predefined policies. For full access, the Root Manage Shared Access Key policy is sufficient for initial setup and learning. Click on it. On the policy page, you'll find the primary connection string and secondary connection string. Copy the primary connection string. Keep this string secure, as it grants full control over your namespace. Introducing the Azure Service Bus Client SDK. To interact with Service Bus from your applications, you'll use a client SDK provided by Microsoft. These SDKs are available for popular programming languages like C, Java, Python, and JavaScript. They abstract away the complexities of the underlying REST API calls, allowing you to focus on sending and receiving messages using high-level methods. While the exact syntax varies slightly between languages, the core concepts remain consistent. For this book, we'll describe the interactions conceptually, focusing on the common principles that apply across all supported SDKs, and occasionally use C# examples for illustration due to its prevalent use in Azure development. The latest generation of Azure SDKs follows a consistent design pattern. Service Bus Client. This is the entry point. You create an instance of this client, typically by passing your connection string or authentication details. It manages the connection to your Service Bus namespace. Service Bus Sender. Created from the Service Bus Client, this class is used specifically for sending messages to a queue or topic. Service Bus Processor or Service Bus Receiver. These classes are used for receiving messages. Service Bus Processor is generally recommended for continuously processing messages. It sets up an event-driven mechanism, automatically managing concurrent message processing and message settlement. Service Bus Receiver allows for more direct, on-demand message reception, which can be useful for specific short-lived operations or when you need more granular control over message receiving loops. You would typically install the relevant SDK package into your project using your language's package manager, e.g., install package Azure Messaging Service Bus for Net, pip install Azure Service Bus for Python. Your first message: sending and receiving. Now, let's put it all together and send our very first message through Service Bus. We'll start by creating a simple queue and then write conceptual sender and receiver applications. 1. Create your first queue. Within your Service Bus namespace, you'll need a queue to send messages to. In the Azure portal, navigate to your Service Bus namespace. In the left-hand menu, under Entities, click on Queues. Click the +Queue button. Provide a name for your queue, e.g., MyFirstQueue. Accept the default settings for now. Important settings like max delivery count, default 10, and message time to live, default 14 days, are critical later, but the defaults are fine for experimentation. You can also enable sessions or duplicate detection here, but leave them unchecked for now. Click Create. Your queue should now be provisioned within your namespace. 2. Sending a message. A sender application prepares a message and dispatches it to the service bus. Conceptual sender code flow. 1. Get your service bus connection string, e.g., from environment variable or configuration. Connection string equals endpoint equals. 2. Specify the name of the queue you want to send messages to. Queue name equals myFirstQueue. 3. Create a service bus client. This client manages the connection to your service bus namespace. Client equals new service bus client, connection string. 4. Create a service bus sender configured for your queue. This sender is responsible for dispatching messages to the specified queue. Sender equals client create sender, queue name, try. 5. Create a service bus message. The message holds the data you want to send. It can be text, JSON, binary, etc. Ensure your message body is encoded appropriately, e.g., UTF-8 for strings. Message body equals hello, Azure Service Bus. Message equals new service bus message, message body. Add optional properties if needed, e.g., for filtering later. Message application properties, message type equals greeting. 6. Send the message. Sender send message async message, print, message sent successfully, plus message body, catch exception. Print error sending message, plus exception message, finally. 7. Clean up resources. It's important to dispose of sender and client when no longer needed. To release connections. In a real application, they might be long-lived. Sender dispose async, client dispose async. When you execute this conceptual code, you should see a confirmation that the message was sent. You can also visit your queue in the Azure portal, and under Overview, you'll see active message count incremented to 1, indicating your message is waiting. 3. Receiving a message. A receiver application connects to the queue, retrieves messages, processes them, and then acknowledges their successful handling. For reliable message processing, Service Bus generally uses a peak lock mode, which we'll focus on. In this mode, when a receiver gets a message, it puts a temporary lock on it, making it invisible to other receivers. Only after the receiver explicitly signals successful processing, by completing the message, is the message removed from the queue. If it fails to complete or abandons the message, the lock is released, and the message becomes available again, and its delivery count increments. Conceptual receiver code flow using Service Bus Processor for continuous listening. 1. Get your Service Bus connection string. Connection string equals endpoint equals. 2. Specify the name of the queue you're listening to. Queue name equals myFirstQueue. 3. Create a Service Bus client. Client equals new Service Bus client, connection string. 4. Create a Service Bus processor. The processor manages receiving messages concurrently and reliably. Processor equals client create processor, queue name. 5. Register message handler. This function or method will be called whenever a message is received. Async function process message, args. Access the message body. Message body equals args message body to string, print, received message. Plus message body, you would add your actual message processing logic here. For example, parsing JSON, updating a database, calling another service. 6. Complete the message. This tells Service Bus that the message has been successfully processed and can be removed from the queue. Await args.complete message async args message, print, message completed. 7. Register error handler. This function or method will be called if an error occurs during processing. Async function process error, args, print, error processing message, plus args exception message. You would typically log this error and potentially trigger alerts. Rethrowing the exception might cause the message to be abandoned. 8. Wire up the handlers to the processor. Processor.process message async equals process message. Processor.process error async equals process error. 9. Start the processor. This begins listening for messages. It will run in the background. Await processor start processing async. Print, processor started, listening for messages. 10. Keep the application running, e.g., wait for user input to stop. In a real application, this might be a long-running service. Console read key. Example. Wait for a key press. Await processor stop processing async. Await processor dispose async. Await client dispose async. When you run this receiver application, it will start listening. The message you sent earlier should be received and processed by this application, and you'll see output confirming its reception and completion. Critically, if you check the Azure portal, the active message count on your queue will now be 0. A note on Service Bus Receiver and Receive and Delete. While Service Bus Processor is recommended for most continuous listening scenarios, you can also use Service Bus Receiver for scenarios where you need more direct control or are fetching messages in batches for one-off tasks. P-clock default and recommended for Service Bus Receiver. You explicitly call Receive Message Async and then Complete Message Async after successful processing. If your application crashes or calls Abandon Message Async, the message returns to the queue. Receive and Delete, not recommended for production. When you receive a message in this mode, it is immediately deleted from the queue. If your application fails after receiving but before fully processing the message is lost. This mode offers slightly higher throughput due to less overhead, but sacrifices reliability. It's rarely suitable for critical business messages. For our examples throughout this book, we will primarily focus on the P-clock mode, implicitly handled by Service Bus Processor or explicitly managed with Service Bus Receiver, because it guarantees reliability and message persistence until successful completion. Conclusion: congratulations! You've successfully navigated the initial setup of Azure Service Bus, understood its different pricing tiers, and, most importantly, sent and received your first message. You now have a working sandbox environment and the basic conceptual understanding to begin building decoupled applications. In the next chapter, we will take a deeper dive into queues. We'll explore their various configurable properties, discuss the lifecycle of a message from creation to completion or dead lettering, and look into basic error handling within your message processing logic. Chapter 3. Queues, the foundation of point-to-point messaging. In the previous chapter, we successfully created our first Azure Service Bus queue and demonstrated the fundamental process of sending and receiving messages. Now, it's time to peel back the layers and understand the true capabilities of Service Bus queues. This chapter will delve deeper into their properties, the intricate life cycle of a message from its creation to its various states, and the critical role of message receivers in ensuring reliable delivery and processing. Queues are the bedrock of reliable point-to-point communication in Service Bus, forming the basis for many robust, asynchronous patterns. Deep dive into Azure Service Bus queues. An Azure Service Bus queue is a storage abstraction where messages are held until retrieved by consumer applications. They implement the first-in, first-out FIFO message delivery characteristic, meaning messages are generally delivered in the order they were sent. However, it's important to note that while messages are enqueued in order, the actual processing order might not be strictly FIFO if multiple consumers are racing to pick up messages, or if messages are deferred or explicitly reordered. For guaranteed strict FIFO, we'll explore message sessions later. When you create a queue, you configure various properties that govern its behavior and lifecycle. Let's look at some of the most important ones. Max size GB. This defines the maximum size of the queue in gigabytes. Once the queue reaches this limit, new messages will be rejected or old messages will be discarded, depending on other settings. For standard tier, maximum size is 80 GB. Premium tier queues can be much larger. Message time to live, MS. This property specifies the maximum duration a message will reside in the queue. If a message is not consumed within this period, it will automatically expire and be moved to the dead letter queue, DLQ. The default is 14 days, or 1,209,600,000 ms. This is vital for time-sensitive messages that lose their relevance after a certain period. Max delivery count. This crucial property determines how many times a message can be delivered to a receiver before it's automatically moved to the dead letter queue. The default is 10. This prevents poison messages, messages that repeatedly fail processing, from indefinitely blocking the queue or causing an infinite loop of failures in consumer applications. Requires session. Discussed in Chapter 5. If enabled, all messages sent to and received from this queue must belong to a session, which guarantees ordered delivery and single consumer processing for a group of related messages. Enable dead lettering on message expiration. Default. Enabled, if a message expires due to TTL, this setting dictates whether it should be moved to the DLQ. If disabled, expired messages are simply deleted. It's almost always recommended to keep this enabled for traceability. Enable dead lettering on message evaluation exception. Default. Enabled applies more to topics and subscriptions where messages might be dead lettered if a filter rules evaluation fails. For simple queues, this is less relevant but good to keep enabled. Duplicate detection history window (MS). Discussed in Chapter 5, if duplicate detection is enabled, this specifies the time window during which service bus checks for duplicate messages based on their message. Lock duration (MS). When a message is received in peak lock mode, the default and recommended method, Service Bus places a temporary lock on it. This lock duration defines how long that lock is held. If the message is not completed or abandoned deferred within this duration, the lock expires and the message becomes available to other consumers. The default is 30 seconds. You can extend this lock during processing. Message states and the lifecycle. Understanding the journey of a message through an Azure Service Bus queue is fundamental to building reliable systems. A message can exist in several states, and consumer actions dictate its progression. Enqueued state, active. A message is in the enqueued state immediately after a sender successfully publishes it to the queue. It's now active and waiting to be picked up by a receiver. This is where its message time to live clock starts ticking. Locked state, pending. When a receiver requests a message using peak lock mode, Service Bus returns the message to the receiver and simultaneously places a temporary lock on it for the queue's configured lock duration. While locked, the message is invisible to other receivers, preventing multiple consumers from processing the same message simultaneously. The message's delivery count is incremented. Settled state, processed, discarded. Once a message is locked, the receiver must settle it. Settlement informs Service Bus about the outcome of the message processing and dictates the message's final destination. There are three primary settlement operations. A. Complete positive settlement. Action, complete a sync message. Outcome, the receiver successfully processed the message. This operation signals to Service Bus that the message is consumed and it should be permanently removed from the queue. Analogy. Like a cashier marking an order as paid and removing it from the open orders list. This is the happy path. B. Abandon negative settlement retry. Action. Abandon a sync message. Outcome. The receiver encountered a transient, temporary, issue and could not process the message at this time. The message's lock is released, and it immediately becomes available again to other receivers, including the same receiver. Its delivery count is incremented. Use cases: network glitches, database timeouts, temporary external service unavailability. Important: if delivery count reaches max delivery count after repeated abandons, the message will be automatically moved to the DL queue. See dead letter, negative settlement, discard, investigate. Action: dead letter async, message, dead letter reason, dead letter description. Outcome: the receiver determined that the message cannot be processed due to a permanent, non-retrievable error, e.g., malformed data, invalid business logic. The message is moved to the dead letter queue, DL queue. Use cases: invalid user input in the message, unrecoverable data integrity issues, messages from a deprecated system. Critical: providing dead letter reason and dead letter description is highly recommended for diagnosis. Defer, special settlement, postpone. Discussed in Chapter 5. Action, defer async message. Outcome: the message is moved to a special sub-queue within the main queue, becoming unavailable for normal reception. It can only be retrieved later by its sequence number. This is for situations where a message needs to be processed later due to some dependency, not because of an error. Dead lettered state, investigation, reprocessing. Messages enter the DL queue either automatically, e.g., max delivery count exceeded, TTL expired, or explicitly via dead letter async. Messages in the DL queue typically require human intervention or a dedicated DL queue processor to analyze the cause, fix the issue, and potentially resend a corrected version to the main queue or archive it. Sending messages. Beyond the basics. In Chapter 2, we showed a simple message send. Let's refine our understanding. A service bus message object isn't just a container for the message body. It has several important properties you can set. Body. The actual content of the message, typically a byte array. For text, ensure it's properly encoded, e.g. UTF-8. It can contain JSON, XML, binary data, etc. Messaged, a unique identifier for the message. While automatically assigned by Service Bus if not provided, it's good practice to assign a custom, application-specific messaged, e.g., a GUID or order ID. If you intend to use duplicate detection or need to correlate messages across systems. Correlationed, used to link messages together in a request-reply pattern or to group messages belonging to the same workflow. It helps trace logical operations across multiple messages. Subject or label, a descriptive tag for the message, helping receivers categorize or filter messages without inspecting the body. Content type, an optional field indicating the MIME type of the body, e.g., application/JSON, text plain. Useful for receivers to parse the body correctly. Time to live, overrides the queue's default time to live for this specific message. Application properties, a dictionary, key-value pairs for custom metadata relevant to your application. This is extremely useful for adding contextual data that receivers can use for routing, filtering, or processing without having to parse the message body. Example, sending a structured message with properties, conceptual. Assuming a product order class or dictionary for message payload. var order details, orderid, XYZ789. Customerid, C456. Product name, deluxe widget. Quantity, 2. Requested delivery date, 2024 to 8 to 15. Convert the product order to a JSON string or byte array. var message body equals JSON stringify, order details. var message equals new service bus message body. Messaged equals order details orderid. Use order ID for correlation tracking. Message.content type equals application/JSON. Message subject equals new product order. Descriptive subject. Add custom application properties. These can be used for filtering messages in topics later, or for carrying lightweight metadata. Message application properties order type equals web purchase. Message application properties priority equals high. Create sender and send message. Receiving messages. Reliability is key. As discussed, pclock is the recommended receive mode. Let's look at the service bus processor again, with a focus on how your handlers should manage message settlement. Receiver application design principles using service bus processor. Atomicity of processing. Your message handler should aim for atomicity. Either the entire processing operation succeeds or it fails. Avoid complex logic where partial success leaves the system in an inconsistent state. Graceful error handling, transient errors. These are temporary issues, e.g., network timeout, database lock, external service momentarily down. For these, you should abandon the message. This releases the message lock and allows Service Bus to redeliver it, respecting the max delivery count. Build in exponential backoff and retry logic in your consumer itself for external calls, and only abandon if the transient error persists. Permanent errors. These are errors that will not resolve with retries, e.g., a malformed message that cannot be parsed, invalid business data, a logic error in your code that would always fail for this specific message. For these, dead letter the message. This moves it out of the main queue, preventing a poison message scenario. Idempotency, crucial, because messages can be redelivered due to abandon, lock expiration, or transient receiver failure. Your message processing logic must be idempotent. This means that processing the same message multiple times should have the same effect as processing it just once. For example, if a message triggers a database insertion, verify if the record already exists before inserting, or use unique constraints to prevent duplicates. We will discuss this further in Chapter 6. Refined conceptual receiver code with error handling. Setup from Chapter 2. Connection string, queue name, client, processor. Async function process message, args. var message equals args message. var message body equals message body to string. Print, received message, ID, plus message messaged plus body, plus message body plus, try. Your message processing logic starts here. Example, parsing a JSON message. var payload equals JSON parse message body, print parsed payload, plus JSON stringify payload. Simulate a transient error, e.g. temporary database outage. If payload simulate transient error, and in message.delivery count 3. Throw new error, simulated transient processing error. Simulate a permanent error, e.g. invalid data. If payload simulate permanent error, throw new error, simulated permanent processing error, invalid data. Your message processing logic ends here. If processing succeeds, complete the message. Await args.complete message async message, print message ID, plus message messaged plus, successfully processed and completed. Catch exception, print error processing message ID, plus message messaged plus exception message. var delivery count equals message.delivery count. var max delivery count equals processor max delivery count. Access this from processor config. Check if error is transient, e.g., network issues, temporary resource unavailability. This usually involves inspecting the exception type or specific error codes. For demonstration, we're using a simulated flag and delivery count. If exception.message. Includes simulated transient processing error and a delivery count max delivery count. Print transient error detected. Abandoning message ID plus message messaged plus for retry. Delivery count plus delivery count. Await args abandon message async message. Message goes back to queue. Else, this is a permanent error, or max, retries exceeded for a transient error. Move message to dead letter queue. var dead letter reason equals processing failed. var dead letter description, message could not be processed due plus, exception message plus. Delivery attempts plus delivery count. Print permanent error or max retries exceeded. Dead lettering message ID plus message messaged plus. Await args.dead letter message async, message, dead letter reason, dead letter description. Async function process error, args. Print unhandleable error in processor source, plus args error source plus, exception, plus args exception message plus. This handler usually logs errors that occur at the processor level, e.g., connection issues or issues within the Service Bus SDK itself. It is not typically for individual message processing errors. Wire up handlers and start processor, as in Chapter 2. Testing the error handling. To test this, you could send a message with simulate transient error. True, observe it being retried a few times and eventually landing in the DL queue. Send a message with simulate permanent error. True, observe it being immediately dead lettered. Send a message with simulate transient error. False, simulate permanent error. False, observe it being processed and completed. By carefully managing the complete, abandon, and dead letter operations, you build resilience directly into your message consumers, ensuring that messages are always either successfully processed or moved to a dedicated area for investigation. Conclusion: you've now gained a solid understanding of Azure Service Bus queues, their key properties, and the life cycle of messages within them. More importantly, you've learned how to design robust message receivers that correctly handle both successful processing and common failure scenarios, preventing message loss and enabling effective troubleshooting through the dead letter queue. Queues provide reliable, one-to-one messaging, which is fundamental for many asynchronous tasks. However, many real-world scenarios require a single event to be distributed to multiple consumers simultaneously. This is where the publish-subscribe pattern, implemented via Azure Service Bus topics and subscriptions, comes into play. We will explore this powerful capability in the next chapter. Chapter 4: Topics and Subscriptions. The power of publish-subscribe. In the previous chapter, we mastered Azure Service Bus queues, establishing a robust foundation for point-to-point, reliable message delivery. Queues excel when you have a defined single receiver or a group of competing consumers working on a shared backlog of tasks, like order processing or email sending. But what if you have an event or piece of information that needs to be consumed by multiple different services, each for their own distinct purpose? This is where the publish-subscribe, pub-sub, pattern, and Azure Service Bus topics and subscriptions truly shine. Imagine a broadcast system. A single message sent by a broadcaster could be picked up by many different receivers, each interested in that specific message for their own unique tasks. This pattern is fundamental to building highly decoupled, scalable, and extensible distributed systems. Understanding the publish-subscribe pattern. The pub-sub pattern involves three main actors: publisher, an application that creates and sends messages, events, or commands to a central intermediary without knowing who or how many consumers there might be. It simply publishes information. Broker, topic. The intermediary, like Azure Service Bus, which receives messages from publishers and routes them to interested subscribers. In Service Bus, this is handled by a topic. Subscriber, an application that expresses interest in specific types of messages by creating a subscription with the broker. When a message matching their interest arrives at the topic, the broker delivers a copy of that message to the subscriber's designated endpoint. The key benefit is the extreme decoupling it offers. The publisher has no direct knowledge of its subscribers, nor do subscribers know about the publisher or each other. They interact solely through the topic, which acts as a central distribution point. This separation of concerns allows for scalability. New subscribers can be added without modifying existing publishers or other subscribers. Extensibility. New features or services can easily plug in to existing event streams by simply creating a new subscription. Flexibility. Different subscribers can consume the same message and process it in entirely different ways. Robustness. If one subscriber fails, it doesn't affect other subscribers or the publisher. Messages generally remain on the topic until all active subscriptions have processed their copies. Creating topics and subscriptions in Service Bus. Just like queues, topics are created within your Service Bus namespace. Each topic can then have one or more subscriptions associated with it. 1. Creating a topic. A topic is the endpoint where publishers send their messages. In the Azure portal, navigate to your Service Bus namespace. In the left-hand menu, under Entities, click on Topics. Click the plus topic button. Provide a name for your topic, e.g., order relevance. Many of the settings for a topic are similar to a queue, e.g., max size, GB, message time to live, MS, enable dead lettering on message expiration. Configure them as needed for your use case. Click Create. Your topic should now be provisioned within your namespace. 2. Creating subscriptions. A subscription is then created on a topic. Think of a subscription as a virtual queue specific to a subscriber. Each message sent to the topic will be delivered to each active subscription. Within the Azure portal, navigate to your newly created topic, order relevance. In the left-hand menu, under Entities, click on Subscriptions. Click the plus subscription button. Provide a name for your subscription, e.g., order processor subscription. Configure its properties. These are very similar to queue properties, but apply per subscription. Max delivery count. Default 10. How many times a message can be delivered to this specific subscription before it's dead lettered for this subscription. Message time to live, MS, overrides the topic's TTL for messages on this subscription. Enable dead lettering on message expiration, whether messages that expire on this subscription go to its DLQ. Lock duration, MS. Duration for locks on messages pulled from this subscription's queue. Require session. Discussed in Chapter 5, enable session handling for messages on this subscription. Crucially, when you create a subscription, it comes with a default rule called default. This rule ensures that all messages published to the topic are delivered to this subscription. We will discuss custom rules, filters, in Chapter 5. Click Create. You can create multiple subscriptions for the same topic. For example, you might create order processor subscription, inventory update subscription, and analytics subscription, all listening to the order relevance topic. Sending messages to a topic. Sending a message to a topic is almost identical to sending a message to a queue. You use the same Service Bus Sender class, but you specify the topic name instead of the queue name during its creation. Conceptual publisher code flow. 1. Get your Service Bus connection string. Connection string equals, endpoint equals. 2. Specify the name of the topic you want to send messages to. Topic name equals order relevance. 3. Create a Service Bus client. Client equals new Service Bus client, connection string. 4. Create a Service Bus sender configured for your topic. Sender equals client create sender, topic name. Try 5. Create a service bus message, e.g., an order created event. var order created event equals event type order created, orderid, ord12345, customerid, CUSD 6789, order date 2024 to 7 to 20T10 30/0Z, total amount 99.99, items producted prod A quantity 1, producted prod B quantity 2. var message body equals JSON stringify, order created event. Message equals new service bus message, message body. Add properties crucial for filtering to be covered in Chapter 5. Message application properties, event type, equals order created. Message messaged equals OC plus order created event ordered. Unique ID for duplicate detection. 6. Send the message to the topic. Sender send message async, message. Print event sent to topic, plus topic name plus message body, catch exception. Print error sending message, plus exception message. Finally, sender dispose async, client dispose async. When this code executes successfully, the order created event message will be sent to the order events topic. Service bus will then make a copy of this message available to every active subscription associated with that topic. Receiving messages from a subscription. Receiving messages from a subscription is functionally identical to receiving messages from a queue conceptually. You use the same service bus processor or service bus receiver class, but you specify the subscription name instead of the queue name. Each subscriber conceptually gets its own separate queue, represented by its subscription. This means that processed messages are removed only from that specific subscription's view of the topic. Delivery counts and dead lettering apply independently to each subscription. If a message is dead lettered on order processor subscription, it can still be active and processed on inventory update subscription and analytics subscription. Conceptual subscriber, receiver, code flow. Let's imagine two different services, order processor and inventory service, both subscribing to the order revents topic. Subscriber 1, order processor service. Setup, connection string, topic name equals order revents. 1. Specify the name of the subscription this receiver is listening to. Subscription name equals order processor subscription. 2. Create service bus client. Client equals new service bus client, connection string. 3. Create a service bus processor for the specific topic and subscription. Processor equals client create processor, topic name, subscription name. 4. Register message handler. Async function process order message, args. var message body equals args message body to string. var event data equals JSON parse, message body. If event data event type equals order created. Print order processor, received order created event for ordered, plus event data ordered, process order. E.g., persist order in database, trigger payment gateway. Print order processor, successfully processed ordered, plus event data ordered, await args.complete message async args message. Else, print order processor, received unhandled event type, plus event data event type plus for ordered, plus event data ordered. In a real scenario, this might abandon or dead letter if unexpected. Await args.complete message async args message, complete to remove from subscription. Register error handler, wire up handlers, and start processor as in Chapter 3. Processor dot process message async equals process order message. Processor dot process error async equals process error. Reuse the error handler from Chapter 3. Await processor start processing async. Print order processor is listening for order events. Keep running. Subscriber 2, inventory service. Setup, connection string, topic name equals order events. 1. Specify the name of the subscription this receiver is listening to. Subscription name equals inventory update subscription. 2. Create service bus client. Client equals new service bus client, connection string. 3. Create a service bus processor for the specific topic and subscription. Processor equals client create processor, topic name, subscription name. 4. Register message handler. Async function process inventory message, args. var message body equals args message body to string. var event data equals JSON parse, message body. If event data event type equals order created. Print inventory service, received order created event for ordered, plus event data ordered. Update inventory for items in the order. For const item of event data dot items. Print inventory service, deducting plus item quantity plus of producted, plus item dot producted. Simulate inventory deduction. Print inventory service, successfully updated inventory for ordered, plus event data ordered. Await args dot complete message async args message. Else. Print inventory service, received unhandled event type, plus event data event type plus for ordered, plus event data ordered. Await args dot complete message async args message. Register error handler, wire up handlers, and start processor as in chapter 3. Processor dot process message async equals process inventory message. Processor dot process error async equals process error. Reuse the error handler from chapter 3. Await processor start processing async. Print inventory service is listening for order events. Keep running. When you run both of these conceptual receiver applications, and then send an order created message to the order events topic, you will observe the following. Both the order processor and inventory service will independently receive a copy of the same order created message. Each one will perform its own specific processing, e.g., order processor saves the order, inventory service updates stock. Each one will complete the message on its own subscription. Completing the message on order processor subscription does not affect the message's status on inventory update subscription. This demonstrates the core power of PubSub. A single event can trigger multiple, distinct, and decoupled workflows. Use case examples of publish-subscribe. Topics and subscriptions are incredibly versatile and form the backbone of many event-driven architectures. Content distribution. A news portal publishes news articles to a newsfeed topic. Different subscribers might update a website, send push notifications to mobile apps, or index the article for search. Event sourcing. Every change in the application state is captured as an event and published to a central topic. Different microservices subscribe to these events to maintain their own read models, integrate with other systems, or perform background processing. Decoupled workflows. In an e-commerce system, an order-placed event can trigger a fulfillment service to prepare the shipment, a payment service to charge the customer, a notification service to send a confirmation email, an analytics service to update sales dashboards. Data replication synchronization. Changes in a master database published as events, with various systems subscribing to synchronize their local copies. Conclusion. Topics and subscriptions empower you to build highly elastic, decoupled, and extensible distributed systems. By embracing the publish-subscribe pattern, your services become autonomous and reactive, leading to more resilient and easier-to-manage architectures. While queues are about one-to-one task distribution, topics are about one-to-many event broadcasting. However, sometimes you don't want all subscribers to receive all messages. You might want to filter messages based on certain criteria, giving certain subscriptions only the messages that are relevant to them. This is where advanced messaging concepts like message filtering, subscription rules, sessions, scheduled messages, and duplicate detection come into play, which we will explore in the next chapter to make your service bus solutions even more sophisticated. Chapter 5, Advanced Messaging Concepts and Patterns. Welcome back to our journey into the world of Azure Service Bus. In the previous chapters, we laid a solid groundwork, exploring the fundamental concepts of queues and topics, and building simple point-to-point and publish-subscribe messaging solutions. You now understand how to send and receive messages, acknowledge their processing, and appreciate the foundational benefits of asynchronous communication. You've taken your first steps towards building decoupled and scalable cloud applications. However, the real world of distributed systems is rarely simple. Messages can encounter unforeseen issues during processing. An order might need to be delayed until a specific future date. A series of related messages might need to be processed strictly in a guaranteed order. And sometimes, you only want certain subscribers to receive specific types of messages from a broader topic, while others safely ignore them. This is precisely where Azure Service Bus truly shines, offering a rich set of advanced features designed to tackle these complex, real-world challenges. In this chapter, we will delve deep into these powerful capabilities. The dead letter Q, DLQ, which serves as a crucial safety net for resilient error handling. Scheduled messages for time-sensitive deliveries. Message deferral for temporarily setting aside messages that aren't yet ready for processing. Duplicate detection for enhancing idempotency. Message sessions for guaranteeing order and managing stateful processing. And subscription rules for finely controlling message flow in publish-subscribe scenarios. Mastering these features will elevate your messaging solutions from merely functional to truly robust, reliable, and intelligent. 5.1 The Dead Letter Q, DLQ. Your message safety net. In any distributed system, messages can occasionally encounter difficulties during their journey or processing. A consumer application might crash, an external service it depends on might be temporarily unavailable, or the message itself might be malformed or contain invalid data. Without a robust error handling mechanism, such failures can lead to messages being endlessly retried and potentially blocking the processing of other valid messages, or worse, being lost altogether. This is precisely why the dead letter Q, or DLQ, is a cornerstone feature of Azure Service Bus, acting as a crucial safety net for your messaging ecosystem. 5.1.1 What is the dead letter Q? At its core, the dead letter Q isn't a separate, explicit queue you create like a standard queue. Instead, it's a sub-queue that is automatically associated with every service bus queue and every subscription to an Azure Service Bus topic. Think of it as a special annex or holding area attached to your main queue or subscription, specifically designated for messages that, for various reasons, cannot be delivered to or processed by their intended receiver. When a message ends up in the DLQ, it signifies that it has been identified as problematic and has been isolated from the regular message flow. This isolation is incredibly valuable for several reasons. Prevents poison messages. A message that consistently causes consumer failure, often referred to as a poison message, will not block the processing of other valid messages in the main queue. By moving to the DLQ, it effectively gets out of the way. Facilitates troubleshooting. Messages in the DLQ are readily accessible for inspection. They retain their original content and properties, but Service Bus additionally injects two important pieces of information: dead letter reason and dead letter description. These provide crucial context about why the message was moved to the DLQ, helping developers and operators diagnose the underlying problem. Enables reprocessing. Once the issue that caused the dead lettering is understood and resolved, or if the message itself can be corrected, messages from the DLQ can be picked up, modified if necessary, and resent to the original queue for another processing attempt. It's important to remember that the DLQ itself is not an error recovery mechanism, but rather an error reporting and staging area. It's the first step in a broader strategy for handling message processing failures, allowing manual intervention or automated resubmission once the root cause is addressed. 5.1.2 Reasons for automatic dead lettering messages. Messages can land in the DLQ automatically under specific conditions that are managed by Service Bus, or they can be explicitly moved there by a receiver application. Understanding these automatic reasons helps in configuring your Service Bus entities appropriately and designing your consumers for robustness. Service Bus automatically scrutinizes messages and moves them to the DLQ in the following common scenarios. Maximum delivery, count exceeded. This is arguably the most common reason for a message to end up in the DLQ. Every queue and subscription in Azure Service Bus has a max delivery count property, which typically defaults to 10. When a message is received in peak-lock mode, the default and recommended mode for reliable processing, it's temporarily locked for a specified lock duration. If the receiver fails to positively acknowledge the message by calling complete async within this duration, or if it explicitly calls abandon async on the message, the lock is released. The message then becomes available again for delivery, and its internal delivery count is incremented. If this delivery count reaches the configured max delivery count limit, Service Bus assumes that the consumer cannot process this particular message successfully, even after multiple attempts. At this point, Service Bus automatically moves the message to the DL queue. The dead letter reason for such messages will be max delivery count exceeded. Consider this scenario. An order processing microservice attempts to process an incoming order message. However, the external payment gateway it needs to call is experiencing a temporary outage. The microservice tries to process the message, fails, and calls abandon a sync. After 10 such attempts, the message reaches its max delivery count and is then automatically moved to the DL queue for manual inspection or later reprocessing. Time to live, TTL, expired. Messages in Service Bus can have a time to live property, which defines the maximum duration they remain valid in the queue or subscription. This is essential for time-sensitive data that loses its relevance after a certain period. If a message is not received and completed within its configured time-to-live duration, it automatically expires and is moved to the DL queue by Service Bus. The dead letter reason will be TTL expired exception. Imagine a system for real-time stock quotes. A message containing a stock price update might only be valid for 60 seconds. If, for some reason, it remains in the queue for longer than 60 seconds without being processed, it's no longer current and automatically moves to the DL queue, ensuring stale data doesn't get processed. Maximum header size exceeded, implicit. While not explicitly listed as a distinct dead letter reason in the same way as max delivery count exceeded, messages with excessively large header properties, including user properties or application properties, might face issues. If a message's header size exceeds the Service Bus's internal limits, it might fail to be sent to the broker in the first place. Or if it manages to be enqueued, it might be problematic for delivery and potentially lead to dead lettering if other limits are hit. This is a less common direct cause of dead lettering, but important to be aware of when adding extensive custom metadata. Session inactivity timeout for session-enabled entities. When working with message sessions, a powerful feature we'll explore later in this chapter, enabling ordered message processing. If a session is locked by a receiver and no new messages arrive for that specific session within its configured session inactivity timeout period, subscription queue session timeout, the session can be closed. If messages remain within that session when it times out and closes, they can also be automatically dead lettered, typically with a reason like session lock lost exception. This signals that the context for those messages has been lost due to session inactivity. Understanding these automatic reasons for dead lettering is crucial for both configuring your Service Bus entities appropriately and designing your consumer applications to differentiate between transient, temporary, retrievable, and permanent, unrecoverable, requiring intervention message processing failures. This informs when to abandon a message versus when to explicitly dead letter it. 5.1.3 Explicit dead lettering. Sometimes, your application can immediately determine that a message is unprocessable due to a permanent, non-retrievable error before exhausting the max delivery count. In such cases, it makes sense to explicitly dead letter the message. This prevents unnecessary retries and quickly moves the problematic message out of the main processing flow. When to use dead letter async? Explicitly. Invalid message format. The message body cannot be parsed, e.g., malformed JSON, corrupted data. Schema mismatch. The message adheres to an outdated or incorrect schema for the current application version. Business rule violation. The message contains data that violates a core business constraint, e.g., order for a negative quantity, invalid customer ID. Pre-existing state. The system is in a state that makes processing this message impossible, e.g., trying to cancel an order that was never placed. When you explicitly dead letter a message, you have the opportunity to provide custom information about why the message was dead lettered. This is invaluable context for troubleshooting. Conceptual explicit dead lettering inside your message processing function. Try, attempt to parse message, var payload equals JSON parse, message body to string. Check for an example business rule violation. If payload quantity 1. This is a permanent business error, not a transient one. Throw new error, order quantity must be positive. Further processing. Await args.complete message async message. Catch E. If E.message. Includes, order quantity must be positive. Explicitly dead letter, due to bad business data. Await args. Dead letter message async. Message. Invalid order data. Order quantity was plus payload quantity plus, which is not allowed. Message ID plus message messaged. Print message explicitly dead lettered plus e-message, else. For other errors, use existing retry logic, abandon or default dead letter. As shown in Chapter 3's error handling. 5.1.4 Processing messages from the DLQ. Messages in the DLQ are not automatically reprocessed. They sit there waiting for intervention. Processing them typically involves viewing in Azure Portal. You can browse the Dead Letter Messages tab on your queue or subscription in the Azure Portal to inspect message content and the dead letter reasons/dead letter description. Programmatic retrieval. You can create a dedicated console application or Azure function that acts as a receiver for the DLQ. The DLQ for a queue is addressed as quename/$dedelterq. For a subscription, it's topic name/subscriptions/subscription name/$dedelterq. Strategies for DLQ processing. Manual intervention. For critical or rare errors, a human operator might analyze the DLQ message, correct the underlying data code, and manually resend the message to the original queue. Automated retry service. For certain types of predictable errors, you might have a service that periodically sweeps the DLQ, applies fixes, if possible, and re-enqueues messages for another processing attempt. Great care is needed here to avoid infinite loops. Alerting and monitoring. The most common first step is to configure Azure Monitor alerts when messages appear in the DLQ, notifying your operations team. Case study example, failed payment processing. An order paid message arrives, but the payment gateway returns an invalid credit card error. The payment processing service immediately dead letters the message with reason, invalid credit card, and description, card X, refused due to invalid number. This message now sits in the order payment DLQ. An alert triggers the support team. They investigate the customer's account, perhaps find a typo in the card number, or advise the customer on a new card. Once the issue is resolved, they can either manually correct and resend the message, or a dedicated payment DLQ processor might pick it up, validate an updated customer profile, and re-enqueue it. 5.2 Scheduled messages. Delivering messages on time. Sometimes you don't want a message processed immediately. You might need to send a reminder next week or trigger a time-sensitive task at midnight. Azure Service Bus allows you to schedule messages for future delivery. 5.2.1 What are scheduled messages? A scheduled message is a message that is sent to a queue or topic, but is held by Service Bus and only added to the active queue subscription for processing at a specified Future Universal Coordinated Time, UTC. 5.2.2 Use cases. Sending reminders. Your appointment is tomorrow at 9 a.m. Delayed actions. A new user signs up, but a welcome email is scheduled to be sent 24 hours later. After a user unsubscribes, their data might be flagged for deletion 30 days later. Deferred tasks. A batch job needs to run at a specific time every day, triggered by a message. Cooling off periods. A customer initiates a refund, but the actual processing is scheduled for 48 hours later, allowing a cooling off period. 5.2.3 Implementing scheduled messages. To schedule a message, you use the scheduled and queue time UTC property of the Service Bus message. Conceptual scheduled message sender. Setup, Service Bus client, Service Bus sender for queue or topic. var message body equals reminder. Your subscription renewal is due tomorrow. var message equals new Service Bus message body. Schedule the message to be available for processing 24 hours from now. var schedule time equals date time UTC now add hours, 24. Message scheduled and queue time UTC equals schedule time. Send the message. Long sequence number equals await sender schedule message async message. Print message scheduled for. Plus scheduled time to string plus sequence number plus sequence number. The schedule message async method returns a sequence number for the scheduled message. This sequence number is crucial if you need to cancel the scheduled message before it's enqueued. The message remains in a scheduled state until scheduled enqueue time UTC is reached. Once that time passes, it transitions to the active queue subscription and becomes available for receivers. You can also cancel a scheduled message before it's enqueued using its sequence number. Setup. Service bus client, service bus sender for queue or topic. Assume sequence number is from a previously scheduled message. Await sender.cancel scheduled message async sequence number. Print scheduled message with sequence number plus has been canceled. Analogy. Scheduling a message is like writing a note to yourself and asking a trusted assistant, service bus, to put it on your active to-do list at a precise future time. 5.3 Message deferral. Pause and resume processing. What if a message arrives, but your application detects that it cannot process it right now, not because of an error, but because some prerequisite isn't met or a dependency isn't available? You don't want to dead letter it because it's not truly invalid, and abandoning it might just lead to repeated immediate retries. This is where message deferral comes in handy. 5.3.1 What is message deferral? Message deferral means taking a message out of the active delivery queue, but keeping it within the same queue, accessible only by its unique sequence number. It's like putting a book back on the library shelf, but writing down its exact location so only you can retrieve it later. 5.3.2 Use cases. Out-of-order messages. A workflow requires messages A, B, and C to be processed in order. If message B arrives before A, you might defer B until A is processed. Temporary resource unavailability. A specific external API, e.g., a credit check API, needed for this message is currently down, but other messages can still be processed. You defer this message until the API is back online. Dependency resolution. A message needs data from another system that is undergoing maintenance. Defer the message until maintenance is complete. Prioritization. A low-priority message could be deferred if high-priority messages are present and need to be processed urgently. 5.3.3 Implementing message deferral. To defer a message, you call defer async on the message. Crucially, the defer async call returns the message's sequence number. You must store this sequence number elsewhere, e.g., in a database, cache, or another queue, if you intend to retrieve the message later, as it's the only way to get it back. Conceptual message deferral. Inside your message processing function. Try. Example, check if a dependency is active, e.g., service X endpoint. If is service X available, defer this message for later retrieval. Await args.defer message async, message. Print message ID plus messaged plus deferred. Sequence number plus message sequence number. Store message sequence number for later retrieval logic. Store deferred message sequence number, message sequence number. Else, process message normally. Await args.complete message async, message. Catch E. Handle other errors, abandon dead letter. To retrieve deferred messages, you use receive deferred messages async by passing a list of sequence numbers. Conceptual retrieval mechanism, e.g., triggered by a cron job or a recovery service. var deferred sequence numbers, get stored deferred message sequence numbers. Retrieve from storage. If deferred sequence numbers .count 0 and an is service X available. 1. Create a service bus receiver for the queue subscription. Receiver equals client create receiver, queue name, or topic name, subscription name for topics. 2. Retrieve the deferred messages. var deferred messages equals await receiver receive deferred messages async, deferred sequence numbers. 4h var deferred message in deferred messages. Print retrieved deferred message with sequence number, plus deferred message sequence number, process deferred message, and then complete abandon dead letter it. Await receiver complete message async, deferred message. Remove stored deferred message sequence number, deferred message sequence number. Clear from storage. Receiver dispose async. Analogy, you're working through your email inbox. You get an email that you can't respond to now because it's missing an attachment. You archive it defer and make a note on a separate list of emails to revisit with the email's ID. Later, when the attachment arrives, you look up the ID and pull the email out of your archive. 5.4 Duplicate detection. Ensuring exactly once processing, almost. In distributed systems, especially those relying on asynchronous communication, it's virtually impossible to guarantee exactly once delivery of messages. Network hiccups, retries by senders, or receiver failures can all lead to the same message being delivered multiple times. While Service Bus aims for at least once delivery, your application often needs exactly once processing. This is where duplicate detection comes into play. 5.4.1 The problem of duplicates. Imagine an order payment system. If an order paid message is processed twice, you might inadvertently charge the customer twice. Or a stock update message processed twice could incorrectly deduct items from inventory. These are unacceptable outcomes. Idempotency, meaning an operation can be applied multiple times without changing the result beyond the initial application, is the ultimate solution. Your consumer must be designed to handle duplicates gracefully. Service Bus duplicate detection acts as a powerful first line of defense. 5.4.2 How Service Bus provides duplicate detection. Service Bus automatically detects duplicate messages for a specified time duration, preventing them from being delivered more than once to the same queue or subscription. To enable it, when creating a queue or topic, set requires duplicate detection to true. Configure the duplicate detection history time window. This is the time span, up to 7 days for standard, up to 14 days for premium, during which Service Bus will remember recently processed messages. Crucially, the sender must set a unique message for each message. If the sender doesn't set it, Service Bus assigns a GUID, but the value differs across retries if the send operation fails and is retried. Thus, for robust duplicate detection, sender's responsibility is to provide application-defined unique value. Conceptual sender with unique message. Setup. Service Bus client, Service Bus sender. var ordered ORD plus GUID new GUID. To string, a unique application level ID. var message body equals JSON stringify. Order ID. Ordered item, widget. var message equals new Service Bus message body. Set a message that is unique for this logical message. Message equals ordered. Await sender send message async message. Print, sent order message with ID. Ordered. If Service Bus receives a message with a message that falls within the duplicate detection history time window and has already been processed or is currently being processed, it will silently discard the duplicate message without delivering it to the queue subscription. The sender's send message async call will still succeed, but the message won't actually appear on the queue. 5.4.3 Limitations and considerations. Not exactly once processing guarantee alone. While Service Bus duplicate detection prevents duplicate delivery to the queue subscription within the window, your consumer must still be idempotent. If the consumer receives a message, processes it, and then crashes before completing it with Service Bus, and the lock duration expires, the message will become available again. If the consumer has no way of detecting that it already processed this message, it might duplicate work. Therefore, use duplicate detection as a strong defense, but build idempotency into your application logic where possible. Performance impact. Enabling duplicate detection incurs a slight performance overhead as Service Bus has to maintain a history of messages. Time window trade-off. A larger history window offers better protection against duplicates, but uses more resources. Choose a window appropriate for your retry policies and potential message delays. 5.5 Message sessions. Guaranteed order and stateful processing. Message queues, by their nature, generally provide best effort ordering. While messages are enqueued in order, the actual order of processing can be lost if multiple consumers are fetching messages concurrently, or if messages are deferred and reinserted. For scenarios where a strict, guaranteed order of messages must be preserved for a logical group, message sessions are indispensable. 5.5.1 What are message sessions? Message sessions allow you to group related messages into a session. All messages belonging to a given session are guaranteed to be delivered and processed by a single consumer instance in the exact order they were sent. Furthermore, Service Bus allows you to maintain session state, a small amount of data directly on the session, accessible only to the active processor of that session. Think of it like a customer service hotline. When you call in, you might get a different agent each time. But if your issue is complex and requires multiple interactions, the system might ensure that all your subsequent calls are routed to the same agent, and that agent has access to your conversation history. Each call would be a message, and all calls related to your specific issue would form a session. 5.5.2 How sessions work. Enable sessions. When creating a queue or subscription, you must set require session to true. Sender sets sessionid. The sender must set the sessionid property on each service bus message. All messages with the same sessionid belong to the same session. Consumer acquires session lock. A session-aware consumer, using a service bus session processor, connects to the queue subscription. Service bus ensures that only one consumer instance at a time can acquire a lock on a specific sessionid. Once a consumer acquires a session lock, it exclusively owns that session until it closes the session, or the session inactivity timeout occurs. Ordered processing. As long as a consumer holds the session lock, all messages for that sessionid are delivered to that same consumer in sequential order. Session state. The session processor can also store and retrieve a small amount of custom session state associated with that sessionid. This state persists as long as the session exists and allows the consumer to maintain context across multiple messages within the same session. 5.5.3 Use cases. User-specific command sequences. Processing user commands, e.g., account creation, profile updates, or actions in a game, in the exact order they were issued by a single user. Conversational flows, building chatbots or interactive voice response, IVR, systems where messages from a single conversation need to be processed sequentially by the same logic instance. Multi-step workflows, managing complex business processes where a series of steps must occur in a specific order for a particular entity, e.g., an order, a financial transaction. Stateful stream processing, aggregating data for a specific entity where intermediate results need to be maintained across messages. 5.5.4 Implementing sessions. Implementing sessions requires using the Service Bus Session Processor in your receiving application. Conceptual sender for sessions. Setup, Service Bus Client, Service Bus Sender for a session-enabled queue topic. Example, sending messages related to a specific user session. var userid user ABC. This will be our sessionid. Message 1, user logs in. var message 1 equals new service bus message, JSON stringify, action. Login, message 1 session id equals userid. Await sender send message async, message 1, message 2, user updates profile. var message 2 equals new service bus message, JSON stringify, action. Update profile data, name, Alice. Message 2 session id equals userid. Await sender send message async, message 2. Message 3, user places order. var message 3 equals new service bus message, JSON stringify, action. Place order data, itemid. P123, message 3 session id equals userid. Await sender send message async, message 3. Print, sent messages for sessionid. Plus userid plus in order. Conceptual receiver for sessions, service bus session processor. Setup, connection string, queue name topic name for session-enabled entity. 1. Create a service bus client. Client equals new service bus client, connection string. 2. Create a service bus session processor. This processor will manage sessions, ensuring one consumer per session in order. Processor equals client create session processor. Queue name, new service bus session processor options. Max concurrent sessions equals 2. How many sessions can be processed concurrently by this instance? Session idle timeout equals timespan dot for minutes 5. Inactivity timeout for a session. 3. Register session message handler. Async function process session message args. var message equals session message args message. var session equals session message args session. Access to the current session object. Print session plus session sessionid plus received message plus message body to string plus sequence plus message sequence number. Get existing session state. var current state equals await session get session state async. var visit count equals current state. Parse int current state to string plus 1 print session plus session sessionid plus current visit count plus visit count, update session state. Await session set session state async, encoding UTF-8. Get bytes, visit count to string. Complete the message. Await session message args, dot complete message async, message. 4. Register session close handler optional. Async function process session closed args. Print session, plus session closed args session ID plus, closed. Reason, plus session closed args reason. You might want to persist final session state here if needed. 5. Register error handler, same as before. Async function process error args, /. 6. Wire up handlers. Processor dot, process message async equals process session message. Processor dot, process session closed async equals process session closed. Processor dot, process error async equals process error. 7. Start the processor. Await processor start processing async. Print session processor started. Listening for sessions. Analogy, message sessions are like a dedicated lane on a highway for a specific type of vehicle. All vehicles of that type, messages with the same session ID, must use that lane, and they will always arrive in the order they entered it. Only one driver, consumer instance, is allowed in that dedicated lane at a time. The session state is like a notepad that driver keeps to remember things about the journey. 5.6. Filtering messages with subscription rules. In our discussion of topics, we mentioned that every message sent to a topic is copied to all its subscriptions. While this is useful, it can be inefficient if subscriptions are only interested in a subset of messages. For example, an email sender service might only care about order-shipped events, not order-created events. This is where subscription rules, also known as filters, come into play. 5.6.1. The need for message filtering. Message filtering allows subscribers to define criteria for which messages they want to receive from a topic. Service Bus applies these rules, and only messages that match the rules criteria are delivered to that specific subscription. This reduces unnecessary message traffic to consumers and allows you to build more focused and efficient services. 5.6.2. How subscription rules work. When you create a subscription, it automatically comes with a default rule, default or true filter, that allows all messages to pass through. You can then add custom rules or replace the default one. Each rule consists of two parts: filter condition, an expression that determines whether a message should pass through. Action optional, an operation that can modify the message properties as it passes through the filter. 5.6.3 Types of filters. Azure Service Bus supports two main types of filters. SQL filter allows you to define SQL-like expressions based on message properties and custom application properties. Examples: message type equals order created. Order ID is not null and quantity 0. Shipper name in FedEx, UPS, and country equals USA. Sys2 equals warehouse, where sys refers to system properties like to, subject, etc. This is the most powerful and versatile filter type. Correlation filter, a simpler filter type that matches messages based on one or more predefined correlation properties, e.g., correlation ID, session ID, message ID, to, reply to, label, content type, and custom application properties. If you set multiple properties in a correlation filter, all of them must match for the filter to pass. Example: a correlation filter set with correlation ID equals myProcessID and label equals step complete will only match messages that have both of these values. 5.6.4 Actions with filters. SQL rule action. A rules action part only applies to SQL filters and allows you to add, alter, or remove properties on a message as it passes through the filter and before it's copied to the subscription. You can set new properties. Set myNewProperty equals value. You can modify existing properties. Set syslabel equals syslabel plus processed. You can remove properties. Remove application property sensitive data. This allows you to enrich messages or clean them up specifically for a given subscriber. 5.6.5 Implementing subscription rules. Rules are created on a specific subscription. Conceptual rule creation. Setup, Service Bus client, topic, and subscription names. Example: subscription for an email service, only interested in order-shipped events. var email subscription name equals email service subscription. Delete the default rule. Await client get subscription, runtime properties async topic name, email subscription name. Get rules client, delete rule async, $default, or delete rule async, true rule.name. Create a new SQL filter rule. var SQL filter equals new SQL rule filter. syslabel equals order shipped. Optionally with an action. var SQL action equals new SQL rule action. Set application properties recipient email equals support@example.com. var rule equals new create rule options. Order shipped email rule, SQL filter, SQL action. Await client get subscription runtime properties async topic name, email subscription name. Get rules client, create rule async order shipped email rule, SQL filter. Print rule order shipped email rule created for subscription plus email subscription name. When a publisher sends any message to the topic, Service Bus will first check the rules for email service subscription. Only if the label, syslabel of the incoming message is exactly order shipped, will a copy of that message be placed into email service subscription. All other messages, e.g., order created, product updated, will be ignored by this subscription. Case study example, e-commerce order events. A topic all order events publishes various events: order created, order shipped, order canceled, payment failed. Shipping service subscription has SQL filter. syslabel equals order created. Only receives new orders to prepare for shipment. Customer notification subscription has SQL filter. syslabel in order shipped, payment failed, order canceled. Only receives events relevant to customer updates. Analytics subscription keeps the default or true filter. Receives all asterisk events for comprehensive data analysis. This precise control over message routing enhances efficiency and allows services to remain focused on their specific responsibilities. Conclusion: you've now explored the truly advanced capabilities of Azure Service Bus, moving beyond basic communication to build sophisticated, resilient, and highly intelligent messaging solutions. The dead letter queue provides critical error handling and traceability. Scheduled messaging and deferral offer granular control over message timing. Duplicate detection is a vital tool for ensuring idempotency, while message sessions enable strong ordering guarantees and stateful processing. Finally, subscription rules unlock powerful message filtering, allowing fine-grained control over message flow in publish-subscribe scenarios. With these advanced patterns in your toolkit, you are well-equipped to design and implement complex asynchronous workflows that are both robust and efficient. In the next chapter, we will deepen our understanding of reliability by focusing on transactional messaging and designing consumers for true message integrity. Chapter 6. Ensuring message reliability and integrity. In the world of distributed systems, messages are not merely data packets. They are often crucial commands, events, or data updates that drive business processes. Losing a message, processing it multiple times, or failing to act upon it due to an error can lead to data inconsistency, financial loss, or a poor user experience. This chapter delves into the critical aspects of ensuring message reliability and integrity in Azure Service Bus, focusing on transactional messaging, understanding delivery guarantees, designing resilient, idempotent consumers, and implementing smart retry policies. Transactional messaging, atomic operations. Atomicity is a fundamental principle in reliable systems. It means that a set of operations either all succeed or all fail together. There is no partial success. Azure Service Bus supports transactional capabilities, allowing you to group send and receive operations into a single atomic unit. Why use transactions? Consider a scenario where your application receives a message, e.g., process order, from QA, performs some processing, and then needs to send two follow-up messages, one to topic B, order processed, and another to QC, inventory deduction. If the application processes the order and sends the message to topic B, but then fails before sending to QC, you've introduced an inconsistency. A transaction ensures that either all three steps, receive from A, send to B, send to C, complete successfully, or none of them do, and the original message remains on QA. How Service Bus transactions work. Azure Service Bus transactions ensure that all operations performed within the scope of a transaction are consistent. If the transaction completes successfully, all operations are committed. If the transaction aborts, all operations are rolled back. Key characteristics. Scope. Transactions are local to a single service bus namespace. You cannot use service bus transactions to span operations across multiple service bus namespaces or other Azure services, like a database. For distributed transactions across multiple services, you would typically look at patterns like the Saga pattern, discussed in Chapter 11, or distributed transaction coordinators, which are more complex. Operations supported. Receive and complete. Receiving a message from a queue or subscription and completing it. Send. Sending messages to a queue or topic. Send via allows for one message to be sent to a queue topic as a result of processing another message atomically. More on this related pattern below. Conceptual transactional operation. Setup, Service Bus Client. Assume client is an instance of Service Bus Client. 1. Create a receiver for the incoming message queue. Incoming receiver equals client create receiver. Incoming orders queue. 2. Create senders for outbound messages. Process sender equals client create sender. Processed orders topic. Inventory sender equals client create sender. Inventory deduction queue. Try. Start a transaction. All operations within the using block are part of the transaction. Await using var transaction equals new service bus transaction. Client. A. Receive a message from incoming orders queue and implicitly complete it within the transaction. Var incoming message equals await incoming receive message async. Max wait time. Timespan dot from seconds 5. Transaction. Associate this receive with the transaction. If incoming message null. B. Perform some processing, e.g., validate order, calculate totals. Var order data equals JSON parse. Incoming message body to string. Print received order plus order date ordered. See send message to processed orders topic. Var processed message equals new service bus message. JSON stringify. Order ID. Order date ordered. Status. Processed. Await processed sender send message async. Processed message. Transaction. Associate this send with the transaction. ID. Send message to inventory deduction queue. Var inventory message equals new service bus message. JSON stringify. Order ID. Order date ordered. Items. Order data dot items. Await inventory sender send message async. Inventory message. Transaction. Associate this send with the transaction. If all operations above were successful, commit the transaction. If any failed, the exception will prevent reaching this line, and the transaction will roll back implicitly when using block ends. Await transaction.commit async. Print. Transaction committed successfully for order. Plus order date ordered. Catch exception. Print transaction failed. Rolling back operations. Plus exception message. Transaction will implicitly abort rollback if commit async is not reached. The original message will return to incoming orders queue. Finally, dispose resources. In a real app, senders receivers might be long-lived. Incoming receiver dispose async. Processed sender dispose async. Inventory sender dispose async. In this example, if the attempt to send to inventory deduction queue fails, the commit async will not be reached, the transaction will roll back, and the original incoming orders queue message will be returned to the queue as if it was never picked up. Send via feature. The send via feature is a specialized form of transaction where the received message is automatically completed or dead-lettered based on the outcome of a subsequent send operation. It simplifies scenarios where the processing of an incoming message consists solely of sending one or more messages to other entities. For example, a message is received from QA, it is then forwarded to QB. Using send via, the completion of the message from QA is tied to the successful sending of the message to QB within one atomic operation. This pattern is primarily useful in complex routing scenarios like message bridges and middleware systems. Message delivery guarantees. Understanding message delivery guarantees is crucial for designing robust systems. No system can guarantee perfect delivery under all circumstances, but Service Bus allows you to aim for different levels of reliability. At most once delivery, meaning a message is delivered 0 or 1 time. It means the message might be delivered successfully or it might be lost. It will not be delivered more than once. In Service Bus, achieved by using the receive and delete mode when consuming messages. As soon as the message is retrieved, it's removed from the queue. If the consumer fails to process it after retrieval, the message is lost. Use case: highly tolerant systems where a small amount of data loss is acceptable, e.g., ephemeral log data, non-critical telemetry. Recommendation: generally not recommended for critical business processes due to the risk of data loss. At least once delivery, meaning a message is guaranteed to be delivered at least one time. It might be delivered more than once if there are failures in acknowledging successful processing. In Service Bus, this is the default and recommended model, achieved by using the pclock receive mode from Chapter 3. When a message is received, it's hidden from other consumers. Only after the consumer explicitly calls complete async is the message removed. If the consumer crashes, the network disconnects, or the lock duration expires before complete async is called, the message returns to the queue and becomes available for redelivery. Use case: most business-critical processes where message loss is unacceptable. Implication: because messages can be redelivered, consumers must be designed to handle duplicates, a concept called idempotency. Effectively exactly once processing, meaning, while exactly once delivery is incredibly difficult to guarantee end-to-end in distributed systems, we can achieve exactly once processing. This means that despite potential multiple deliveries, the effect of processing the message occurs only once. In Service Bus, this is achieved by combining at least once delivery using pclock with duplicate detection from Chapter 5, ensuring the broker doesn't redeliver within a window, and most critically, designing idempotent consumers. This combination provides a strong guarantee against duplicate side effects. Designing idempotent consumers. As discussed, at least once delivery means your consumer might receive the same message multiple times. To avoid adverse side effects, like charging a customer twice or duplicating an inventory deduction, your message processing logic must be idempotent. An idempotent operation is one that, when applied multiple times, produces the same result as applying it just once. Strategies for idempotency. Unique request IDS/action identifiers. Every message should carry a unique identifier for the specific operation it represents, e.g., messaged and ordered, or a unique transactioned. Before performing any side effects, the consumer should check if an operation with that ID has already been successfully completed. Conceptual example: function process payment message, var paymented equals payment message messaged, or a custom ID inside the body. Check if this payment process has already been done. If payment status services payment processed, payment ID, print payment plus paymented plus, already processed. Skipping, return, do nothing operation is idempotent. Perform payment processing, e.g., call external payment gateway. Mark as processed, e.g., store paymented in a database after success. Payment status service mark payment as processed, payment ID. Print payment plus paymented plus, processed successfully. Conditional updates. When updating records in a database, use conditional clauses, where clauses, that check the current state before applying changes. Example, SQL. Instead of update account set balance equals balance 100 where accounted equals XYZ, use update account set balance equals balance 100 where accounted equals XYZ and last processed messaged, new messaged. This ensures the update only happens if it's based on a newer message. Unique constraints. Leverage unique constraints in your database for critical operations. If an insert operation attempts to add a record with a duplicate unique key, the database will throw an error, preventing the duplicate. Example, when creating an order, ensure your database orders table has a unique constraint on ordered. If ordered is derived from messaged, attempting to insert the same messaged twice will fail. Transaction logs, outbox pattern. For more complex scenarios, especially when a message triggers changes across multiple systems, the outbox pattern is very robust. All changes, database updates, messages to send, are written atomically to a temporary outbox table within your local database transaction. A separate process then reads from the outbox and publishes the messages. If that process fails, it picks up where it left off, and messages already published are handled by Service Bus's duplicate detection and the consumer's idempotency. Building idempotent consumers is not an optional extra. It's a fundamental requirement for reliable message processing in at least once delivery systems. Handling transient errors and implementing robust retry policies. Even the most robust applications encounter transient errors. These are temporary, self-correcting faults that resolve themselves without human intervention. Examples include brief network glitches, a temporary database connection drop, or an external API hitting a rate limit. Transient versus permanent errors, the distinction. Transient errors, temporary, expected to resolve on their own, suitable for retries. E.g., timeout exception, SQL exception related to connection, API rate limit. Permanent errors, non-recoverable, indicate a fundamental problem. Not suitable for retries, should lead to dead lettering. E.g., format exception due to malformed message, argument exception due to invalid business data, unauthorized access exception due to invalid credentials. Retry policies for transient errors. When a transient error occurs, the consumer should not immediately dead letter the message. Instead, it should abandon the message, as discussed in Chapter 3. This releases the message lock and makes it available for redelivery. The consumer, or another instance of the consumer, can then try again. To prevent overwhelming the system or indefinitely retrying a problem, retry policies are crucial. Fixed interval retries. Retries occur at a constant interval, e.g., every 5 seconds. Pros: simple to implement. Cons: can overwhelm a recovering system, especially if many operations are retrying simultaneously. Linear backoff: each retry waits for a fixed amount longer than the previous, e.g., 5s, 10s, 15s. Pros: spreads out retries. Cons: still predictable and can cause thundering herd problems if many processes retry at similar rates. Exponential backoff with jitter, recommended. The most robust and commonly recommended strategy. Each successive retry waits for an exponentially increasing period. Jitter: a small, random delay is added to the waiting period. This prevents all failing requests from retrying simultaneously, the thundering herd problem, distributing the load, and allowing the recovering system to truly recover. Example delays: 1s, 2 to 3s, 4 to 8s, 8 to 16s, etc. Implementation: many SDKs and libraries, like Poly4Net, provide built-in support for exponential backoff with jitter. Integration with Service Bus Max Delivery Count. Service Bus's Max Delivery Count setting, from Chapter 3, works in conjunction with your retry policy. If your consumer encounters a transient error and abandons the message, its delivery count increments. After max delivery count attempts, Service Bus will automatically move the message to the dead letter queue. This serves as a safety net, preventing messages from being stuck in an infinite retry loop due to a persistently flaky dependency or a misconfigured retry policy. Conceptual consumer with integrated retry logic. Inside your message processing function, updated from Chapter 3. var message equals args message. var delivery count equals message.delivery count. var max delivery count equals await processor get queue runtime properties async. Max delivery count, get queue's max delivery count. Try, attempt processing. Await args.complete message async message, print, message processed and completed. Catch exception. If is transient error, exception, and in delivery count max delivery count. Implement exponential backoff, but delay before abandoning. In a real application, you might use a retry library. For illustration, we're just recording the intent to retry. Print, transient error, plus exception message plus, will retry, delivery attempts, plus delivery count, await args abandon message async, message. Message returns to queue for redelivery. Else, permanent error or max delivery count exceeded, dead letter. var dead letter reason equals is transient error, exception, max delivery count exceeded, permanent processing error. Var dead letter description equals exception message plus, delivery attempts, plus delivery count. Print dead lettering message. Reason, plus dead letter reason. Await args.deadletter message async, message, dead letter reason, dead letter description. Function to check if an exception is transient, simplified for concept. Function is transient error, x. Return x.message.includes, network, x.message.includes, timeout, x.message.includes, temporarily unavailable. In a real app, this function would inspect specific exception types and error codes by carefully distinguishing between transient and permanent errors and applying appropriate retry policies orchestrated with abandon and max delivery count. You ensure that your message processing system is both robust and resilient. Conclusion: ensuring message reliability and integrity is paramount for any aspiring distributed system. In this chapter, we explored how service bus transactions provide atomicity for operations within a single namespace, preventing partial failures. We demystified message delivery guarantees, at most once, at least once, and effectively exactly once processing, highlighting the crucial role of designing idempotent consumers. Finally, we discussed how to handle transient errors through robust retry policies, especially exponential backoff with jitter, and integrate them with service buses' built-in max delivery count feature to build truly self-healing message processing pipelines. With these mechanisms in place, you are well on your way to building message-driven architectures that can withstand the inevitable challenges of distributed computing. In our next chapter, we'll shift our focus to securing your service bus resources, ensuring that your valuable messages are protected from unauthorized access. Chapter 7. Security and Access Control. In the cloud, security is not an afterthought. It's a foundational concern. Azure Service Bus, as a critical component for inter-service communication and data flow, requires robust security measures to protect your sensitive messages and prevent unauthorized access or manipulation. This chapter will guide you through the various security features offered by Azure Service Bus, from identity-based authentication to network isolation, ensuring your messaging infrastructure is hardened against threats. Shared Access Signatures, SAS, the traditional approach. For a long time, shared access signatures, SAS, were the primary method for authenticating access to Azure Service Bus. While still supported and sometimes used, especially in scenarios involving external or third-party applications, they are increasingly being superseded by Azure Active Directory, AAD, integration for Azure native applications. How SAS works: a shared access signature, SAS, is a URI that grants restricted access rights to your service bus resources for a specified period and with specific permissions. It consists of the resource URI, the access policy name, the access key, and an expiration. Shared access policies. On a service bus namespace, queue, or topic, you create shared access policies. Each policy defines a set of permissions, e.g., send, listen, manage. Manage grants full control, including creating deleting entities. Send grants permission to send messages. Listen grants permission to receive messages. Typically, you'd create separate policies for senders and receivers, granting them only the necessary permissions, e.g., sender policy with send rights, receiver policy with listen rights. Primary secondary keys. Each shared access policy has a primary and secondary key. These are essentially cryptographic secrets that Service Bus uses to verify the SAS token. Connection string. The connection string you used in earlier chapters, e.g., endpoint equals shared access key name equals root manage shared access key equals, is a pre-generated SAS key. Security considerations with SAS. Key management. SAS keys are long-lived secrets. If a key is compromised, it grants unauthorized access until it's regenerated or the policy is deleted. Regenerating a key can be disruptive as all applications using that key will need to be updated. Expiration management. While SAS can be generated with an expiration, managing the lifecycle and rotation of these tokens can be complex, especially for large-scale deployments. No identity. SAS tokens are not tied to a specific user or application identity. They grant access to anyone who possesses the token, making auditing and revocation challenging. Scope. SAS can be granted at the namespace level, which applies to all queues topics within it, or granularly at the queue topic level. Always grant the minimum necessary permissions and scope. Recommendation: while useful for quick starts or specific third-party integration points, for Azure native applications, Azure Active Directory (AAD) with role-based access control (RBAC) is generally the preferred and more secure approach. Azure Active Directory (AAD) integration, identity-based access. Azure Active Directory (AAD) provides identity and access management for Azure resources. Integrating Service Bus with AAD allows you to grant permissions based on the identity of the user or application, leveraging familiar RBAC, role-based access control, principles. This is the modern, enterprise-recommended approach for securing Azure services. How AAD integration works: instead of using a shared secret SAS key, your application authenticates with AAD and obtains an access token. This token, representing the application's identity, is then presented to Azure Service Bus for authorization. Identities, user identities, for developers or administrative tasks, e.g., performing management operations on a Service Bus namespace via Azure CLI or PowerShell. Service principals, for applications deployed outside of Azure, e.g., an on-premises application. Managed identities, the most secure and easiest way for applications running within Azure, e.g., Azure Functions, App Services, VMS, to authenticate. Azure automatically manages the lifecycle of these identities, removing the need to manage credentials yourself. Role-based access control, RBAC. Azure defines several built-in RBAC roles for Service Bus. You assign these roles to AAD users or managed identities. Azure Service Bus Data Owner grants full access to Service Bus entities, queues, topics, subscriptions, and their data, including managing rules, sessions, etc., equivalent to manage rights on SAS. Azure Service Bus Data Sender grants permission to send messages to queues and topics, equivalent to send rights. Azure Service Bus Data Receiver grants permission to receive messages from queues and subscriptions, equivalent to listen rights. Azure Service Bus Data Contributor grants send and receive rights. You can assign these roles at the namespace, resource group, or subscription level, applying the principle of least privilege. Authentication Flow Managed Identities. Your Azure application, e.g., Function App, has a managed identity enabled. You grant the managed identity the appropriate Service Bus RBAC role, e.g., Azure Service Bus Data Sender, on your Service Bus namespace. Your application's Service Bus Client SDK automatically uses the managed identity to acquire an AAD token and authenticate with Service Bus. No connection string with secrets is required in your code or configuration. Conceptual SDK initialization with managed identity. Instead of using a connection string, for applications using managed identity, e.g., Azure Function App Service, the default Azure credential will automatically pick up the managed identity credentials. var client equals new Service Bus client. Your -service bus -namespace .servicebus.windows.net. New default Azure credential authenticates using the managed identity. To then create sender receiver as usual. var sender equals client create sender. MyQ. Using default Azure credential is the recommended approach as it supports multiple authentication methods and automatically selects the most appropriate one based on the environment, e.g., managed identity in Azure, developer credentials locally. Benefits of AAD RBAC. Centralized identity management. Use your existing AAD identities and groups. Reduced credential management. Eliminates the need to store and rotate SAS keys in your application code or configuration. Managed identities handle this automatically. Fine-grained permissions. Grant precise permissions at different scopes, namespace, queue, topic. Improved auditing. AAD provides detailed audit logs of who accessed what when. Security best practices. Aligns with cloud security best practices by using identity-based access control. Recommendation. Always use AAD RBAC with managed identities for Azure-hosted applications accessing Azure Service Bus. Network security. Isolating your Service Bus. Beyond authentication, controlling network access to your service bus namespace is another critical layer of security, especially for sensitive data. Azure Service Bus offers features to restrict network access, ensuring that only trusted networks or services can communicate with your messaging endpoints. 1. IP filtering rules. Purpose allows you to define a set of IP addresses or IP ranges that are permitted or denied access to your service bus namespace. How it works. You configure rules similar to firewall rules to specify which incoming public IP addresses can connect. Use cases, restricting access to internal corporate networks, specific VPN gateways, or known public IP addresses of trusted partner systems. Configuration, found under Networking settings of your service bus namespace in the Azure portal. You can allow specific IP ranges and/or allow access from Azure services, like Azure functions that don't have static IPs. 2. Virtual Network (VNet) service endpoints. Purpose: securely connects your Azure Virtual Networks (VNets) to your service bus namespace over the Azure Backbone network, bypassing the public internet. This provides virtual network isolation. How it works. Enabling a service endpoint on your VNet for Service Bus extends your VNet's identity to the Service Bus service. Service Bus can then restrict access to traffic originating from selected subnets within your VNet. Use cases. When you have Azure VMS, app services, or functions deployed within a VNet, and you want to ensure their communication with Service Bus remains entirely within the private Azure network, enhancing security and reducing exposure to the public internet. Drawback: while the traffic flows over the private network, the Service Bus endpoint itself is still publicly accessible, albeit restricted by the VNet service endpoint configuration. 3. Private endpoints, recommended for highest security. Purpose: provides the most secure way to connect to your service bus namespace. It creates a private IP address for your service bus within your Azure VNet, effectively bringing the service bus into your private network. All traffic then flows over this private connection, never traversing the public internet. How it works. A network interface, NIC, is provisioned within your VNet, assigning a private IP address from your VNet's address space to your service bus endpoint. DNS resolution for your service bus endpoint will then resolve to this private IP address. Use cases. For critical enterprise applications handling sensitive data, or when strict compliance requirements mandate complete private network isolation. It's the go-to solution for truly isolating your service bus. Requirement: requires the Service Bus Premium tier. Conceptual comparison of network security. Feature description best for requirements. IP filtering allows denies traffic based on source public IP addresses. Simple network control for known public IPs. Any tier. VNet service endpoints extends a VNet's identity to Service Bus, allowing access restriction to specific VNet subnets over Azure Backbone. Public endpoint remains, isolating traffic from Azure VNet resources, bypassing public internet. Any tier. Private endpoints creates a private IP address for Service Bus within your VNet, making it accessible only privately. No public endpoint. Highest security, complete private network isolation for critical apps. Premium tier only. Best practice. Combining AAD-RBAC for authentication with private endpoints for network isolation provides the most robust security posture for your Azure Service Bus deployments. Best practices for securing Service Bus. Least privilege. Grant users and applications only the minimum necessary permissions. Don't give a sender application manage rights or listen rights if it only needs to send. Managed identities first. For Azure-hosted applications, always use managed identities for authentication. Eliminate embedded secrets, connection strings in your code or configuration. Private endpoints for critical workloads. For production systems handling sensitive data, leverage private endpoints, requiring premium tier to ensure traffic never leaves your private VNet. IP filtering. Use IP filtering as a basic line of defense for public-facing Service Bus endpoints or to restrict access from specific external locations. Regularly review access. Periodically audit who has access to your Service Bus resources and what permissions they have. Monitor access and auditing. Use Azure Monitor logs to track access and operations on your service bus namespace. Look for unusual activity or unauthorized access attempts. Key rotation. If using SAS. If you must use SAS, implement a strategy for regular key rotation to minimize the impact of a compromised key. Conclusion. Securing your Azure Service Bus is paramount to protecting your distributed applications and the sensitive data they exchange. By embracing Azure Active Directory with role-based access control, especially through managed identities, you move towards a modern, identity-driven security model that eliminates the complexities and risks associated with shared secrets. Further enhancing this with network isolation features like IP filtering, virtual network service endpoints, or the highly secure private endpoints, you can build a multi-layered defense around your messaging infrastructure. Understanding and applying these security best practices will ensure your Azure Service Bus solutions are not just robust and scalable, but also resilient against unauthorized access and threats. In the next chapter, we will shift our focus to monitoring and managing your service bus operations, ensuring visibility and control over your messaging system. Chapter 8. Monitoring, Management, and Operations. A robust messaging system is not just about sending and receiving messages. It's about ensuring your system operates smoothly, identifying issues before they become critical, and having the tools to manage your messaging entities effectively. This chapter delves into the operational aspects of Azure Service Bus, focusing on how to monitor its health and performance using Azure Monitor, manage your entities programmatically, and address common operational considerations like scaling and disaster recovery. Azure Monitor, your messaging system's dashboard. Azure Monitor is a comprehensive solution for collecting, analyzing, and acting on telemetry from your cloud and on-premises environments. For Azure Service Bus, it provides invaluable insights into the performance, health, and availability of your namespaces, queues, topics, and subscriptions. Azure Monitor primarily provides two types of telemetry for Service Bus. Metrics, numeric values that describe some aspect of the system at a particular point in time. Metrics are lightweight and support near real-time scenarios, making them ideal for alerting. Logs, event data that captures detailed information about resource operations, activities, and potential issues. Logs are more verbose and are used for deeper analysis and troubleshooting. Key Service Bus metrics. Numerous metrics are available for Service Bus, helping you monitor its health and performance. Messages, incoming messages, number of messages sent to the Service Bus. Outgoing messages, number of messages delivered by the Service Bus to consumers. Active messages, number of active messages in a queue subscription waiting to be consumed. Dead letter messages, number of messages in the dead letter queue. Scheduled messages, number of messages scheduled for future delivery. Size bytes, the current size of the queue topic subscription. Requests and throttling, successful requests, number of successful API calls to Service Bus. Server errors, number of server-side errors, Service Bus internal issues. User errors, number of client-side errors, e.g. bad requests, authorization failures. Throttled requests, number of requests that were throttled due to exceeding Service Bus limits, e.g. bandwidth, operations per second. This metric is critical for identifying potential bottlenecks and scaling needs. Connections, active connections, current number of open connections to the Service Bus. Monitoring with metrics, dashboards, and alerts. You can visualize these metrics in the Azure portal using Azure Monitor dashboards. Create custom dashboards to get an at-a-glance view of your critical Service Bus metrics, such as active message counts, incoming-outgoing rates, and dead letter queue growth. For proactive monitoring, alerts are essential. You can configure alerts based on metric thresholds. For example, high active message count. Alert if active messages in a critical queue exceeds a certain threshold, e.g., 1,000 messages for more than 5 minutes. This indicates a consumer bottleneck or failure. Growing dead letter queue, DLQ, alert if dead letter messages starts increasing consistently. This signals messages failing to process, warranting immediate investigation. Throttling. Alert if throttled requests rises significantly. This means your service bus is under too much load or you're hitting usage limits, potentially impacting application performance. Low outgoing messages / high incoming messages. A disparity might indicate consumers are failing or not scaling adequately. Alerts can trigger various actions, such as sending email notifications, SMS, pushing to a webhook, or automatically executing an Azure function or Logic app to address the issue. Diagnostic settings and logs. For deeper analysis and auditing, configure diagnostic settings for your service bus namespace. This allows you to route service bus logs to Log Analytics Workspace. For powerful querying and retention of logs, this is the most common destination for production environments. Storage Account, for archiving logs for long-term retention. Event Hubs, for streaming logs to external SIEM systems or custom processing engines. Once logs are in a Log Analytics Workspace, you can use Kusto Query Language, KQL, to query the data. For example, find all authorization failures, Azure Diagnostics, where resource provider microservices, where category operational logs, where operation name authorization failed. Track message, send receive operations per entity. Azure Diagnostics, where resource provider microservices, where category operational logs. Summarize count by operation name, entity name, managing service bus entities programmatically. While the Azure portal is great for initial setup and quick checks, for automation, large-scale deployments, or dynamic management, you'll want to manage your service bus entities programmatically. Azure provides excellent tools for this. Azure CLI command line interface, as Service Bus namespace, create delete list namespaces, as Service Bus queue, create delete list queues, update queue properties, as Service Bus topic, create delete list topics, configure properties, as Service Bus topic subscription, create delete list subscriptions, rules, use case, scripting infrastructure as code, CI/CD pipelines, quick administrative tasks. Azure PowerShell, new as Service Bus namespace, get as Service Bus queue, set as Service Bus topic, etc. Offers similar capabilities to Azure CLI, but with PowerShell syntax and object-oriented output. Use case, highly integrated with other Azure PowerShell CMDlets, preferred by IT pros familiar with PowerShell. Service Bus Management SDK, available for Net, Java, Python, and JavaScript. These SDKs allow you to programmatically create, update, delete, and inspect the properties of service bus entities from within your applications. Use case, building custom management tools, self-healing systems that create queues on demand, or dynamic configuration updates. Example, conceptual, using Azure Messaging Service Bus Administration. Create an admin client, requires manage, permissions, or specific RBAC role. Admin client equals new Service Bus Administration client, connection string. Check if a queue exists. If await admin client queue exists async, my new order queue. Define queue properties. var queue options equals new create queue options, my new order queue. Max delivery count equals 5. Default message time to live equals timespan dot from days, 7. Require session equals false. To create the queue, await admin client create queue async, queue options, print, queue my new order queue created. Get queue runtime properties, active message count, etc. var runtime properties equals await admin client get queue runtime properties async, my existing queue. Print queue my existing queue has plus runtime properties active message count plus active messages. Operational considerations. Moving beyond individual entity management, there are broader operational concerns when running Service Bus in production. Scaling. Azure Service Bus offers various ways to scale to meet demand. Consumer scaling. The most common way to scale is by increasing the number of active consumer instances for a queue or subscription. Since Service Bus allows multiple receivers for a single queue subscription, with message locking, adding more instances automatically distributes the message processing load. Partitioning, premium tier. In the premium tier, you can enable partitioning for queues and topics. Partitioning distributes the queue or topic across multiple message brokers within the Service Bus, providing higher throughput and improved availability. Messages are distributed across partitions based on their hash or sessioned if sessions are used. Messaging units, premium tier. The premium tier allows you to select messaging units, MUs. MUs represent a fixed set of dedicated resources, CPU, memory, storage, and provide predictable throughput. You can scale MUs up or down dynamically to handle varying workloads and ensure consistent performance. Scaling best practice. Start by scaling your consumers. If consumers are still backlogged and service bus metrics, like throttling, incoming-outgoing rates, indicate a service bus bottleneck, then consider scaling up service bus itself, e.g., increasing MUs or adopting partitioning in premium. Disaster recovery and business continuity. While Azure Service Bus is highly available by design within a single region, regional outages can occur. For mission-critical applications, planning for disaster recovery is essential. Geodisaster recovery, premium tier. This feature provides automatic disaster recovery capabilities by pairing a primary service bus namespace with a secondary namespace in a different Azure region. It maintains a fully synchronized copy of the namespace metadata, queues, topics, subscriptions, rules. It does not replicate messages themselves. Messages reside in the active namespace. In the event of a regional outage or a planned failover, you can initiate a managed failover. All traffic is then routed to the secondary namespace. Your applications still connect to the same alias, fully qualified domain name, so client configuration changes are not required. It minimizes data loss if your primary region becomes unavailable, but some in-flight messages might be lost, those not yet processed by your application. Active-active or active-passive custom implementations. For non-premium tiers or scenarios requiring full data replication and zero data loss, you might build custom disaster recovery solutions. This often involves deploying service bus instances in multiple regions, sending messages to both regions, active-active, replicating messages between regions using tools like Azure Functions or Event Hubs. This is significantly more complex to implement and manage than the built-in GeoDR. Doctor best practice. For critical production workloads, the premium tier's built-in geodisaster recovery offers a robust and managed solution. Understand its limitations, no message replication, and design your applications accordingly. Troubleshooting common service bus issues. When things go wrong, here are common areas to check. Messages stuck in queue/DLQ growing. Cause: consumers are down, slow, or constantly failing. Troubleshoot. Check consumer application logs, CPU memory, network connectivity. Monitor active message count and dead letter messages metrics. Throttling. Cause: exceeding namespace or entity limits, bandwidth, operations per second, connection count. Troubleshoot. Monitor throttled requests metric. Scale up service bus, MUs, partitioning, optimize message batching, increase consumer concurrency, or review application design. Authorization failures. Cause: incorrect SAS keys, expired tokens, incorrect AAD/RBAC roles, misconfigured network rules. Troubleshoot. Check application connections, strings, managed identity configuration, AAD audit logs, service bus user errors, and authorization failed logs in Azure Monitor. Message loss/duplicates. Cause: unhandled exceptions in consumers, receive and delete mode, lack of idempotency, short lock duration. Troubleshoot. Ensure consumers use pclock and complete async. Verify idempotency. Check max delivery count setting. Review diagnostic logs. Connectivity issues. Cause: firewall rules, network misconfigurations, DNS issues, service outages. Troubleshoot. Check IP filtering, VNet integration, private endpoint configuration. Ping DNS endpoint. Check Azure Service Health. Conclusion. Operating Azure Service Bus in production goes beyond mere message exchange. It requires proactive monitoring, effective management of your entities, and a solid plan for scaling and disaster recovery. Azure Monitor provides the visibility needed to understand your system's health, while the CLI, PowerShell, and Management SDKs empower you to automate operational tasks. By understanding how to scale Service Bus and implementing robust disaster recovery strategies, you can ensure your critical messaging infrastructure remains highly available and performs optimally, even under challenging conditions. In the next chapter, we will look at how Azure Service Bus integrates seamlessly with other Azure services to build powerful, event-driven solutions. Chapter 9. Integrating Service Bus with Azure Services. Azure Service Bus, powerful as it is on its own, truly unlocks its potential when integrated with other services within the Azure ecosystem. By combining Service Bus with complementary services like Azure Functions, Logic Apps, and Event Grid, you can build sophisticated, event-driven architectures that are highly scalable, cost-effective, and responsive. This chapter explores common integration patterns, demonstrating how Service Bus acts as a central nervous system, connecting various parts of your Azure solution. Azure Functions. The serverless bridge to Service Bus. Azure Functions are a serverless compute service that allows you to run small pieces of code, functions, without managing infrastructure. They are a natural fit for processing messages from Service Bus or sending messages to Service Bus due to their event-driven nature and consumption-based pricing model. How Azure Functions integrate with Service Bus. Azure Functions provide two primary mechanisms for Service Bus integration. Service Bus Trigger. A function can be configured to execute automatically whenever a new message arrives in a specified Service Bus queue or subscription. The function runtime handles receiving the message, locking it peak lock, and automatically completing it if the function executes successfully or abandoning dead lettering it if the function throws an unhandled exception or its execution times out. This significantly simplifies the receiver code. Use cases: processing incoming orders, handling user registrations, executing background jobs from queues, reacting to events from topics. Service Bus Output Binding. A function can output messages directly to a Service Bus queue or topic. This allows the function to serve as a publisher or a forwarder of messages. Use cases. After processing an incoming message, a function can send a completion event to another queue topic or forward a message to a different Service Bus entity. Example: order processing with Azure Function Trigger. Let's imagine an order-created message arrives in a Service Bus queue. An Azure function can be triggered to process this order. Conceptual Azure Function Order Processor, triggered by Service Bus Queue. Assuming a Service Bus queue named Orders Queue. Function name, Order Processor. Public static async task run. Service Bus Trigger, Orders Queue, connection equals Service Bus connection, string my queue item. iLogger log. Log information. $C# Service Bus Queue Trigger function processed message. My queue item, try. Deserialize the message, e.g. JSON. var order equals newtonsoft.json.json, convert.deserialize object order. My queue item. Your business logic. Example: validate order, store in database, call external payment gateway. Log information, $processing order ID, orderid for customer, order customerid. Simulate some work. Await task.delay 1000, end business logic. If the function completes successfully, the message is automatically completed, peak lock mode. Log information, orderid processed successfully. Cat exception X. If an unhandled exception occurs, the message will be defaulted to abandon, based on max delivery count. Azure Functions will respect the max delivery count on the ASBQ subscription, and eventually dead letter the message if processing consistently fails. Log error, $error processing message, X message, rethrow to signal failure, and trigger message redelivery dead lettering. Public class order, example simplified order class. Public string orderid get, set. Public string customerid get, set. Public decimal total amount get, set. Benefits, cost effective. You only pay for the compute time your function uses. Scalability. Azure Functions automatically scale out, add more instances based on the number of messages in the queue, handling high-throughput scenarios effortlessly. Reduced boilerplate. The function runtime handles much of the message management, locking, completing, error handling logic with max delivery count, allowing you to focus on business logic. Logic Apps and Power Automate. Low-code workflow orchestration. Azure Logic Apps and Power Automate, built on the same engine. are cloud-based services that help you schedule, automate, and orchestrate tasks and workflows across applications, data, cloud services, and on-premises systems. They offer a visual designer, low-code, no-code, for building workflows, and like Azure Functions, they have deep integration with Service Bus. How Logic apps integrate with Service Bus. Logic apps provide rich connectors for Service Bus. Service Bus triggers. When a message is received in a queue, autocomplete. When a message is received in a queue, peak lock. When a message is received in a topic subscription, autocomplete, peak lock. These triggers initiate a Logic app workflow when a new Service Bus message arrives. Service Bus actions. Send message to a queue topic. Complete the message in a queue subscription. Abandon the message in a queue subscription. Dead letter the message in a queue subscription. Defer the message in a queue subscription. These actions allow the Logic app to interact with Service Bus at various points within the workflow, sending new messages or settling received messages. Example, automated email notification for failed orders. Consider a scenario where orders failing to process and subsequently dead-lettered need to trigger an email notification to operations. Conceptual Logic app workflow. Trigger, when a message is received in a topic subscription, peak lock. Subscription, failed order subscription to order processing topic $dead queue. Yes, you can subscribe to dead letter queues. Action 1, optional compose data. Compose, input, parse trigger body to extract relevant order details and the dead letter reason. Action 2, email. Send an email Office 365 Outlook /send grid /etc. to operations@yourcompany.com. Subject, urgent. Failed order, parse dead letter reason. Body, order parsed ordered, failed processing due to, parse dead letter reason. Full details, parsed message body. Please investigate. Action 3, conditional complete message. Condition. If email sent successfully, complete the message in a queue subscription for the dead-lettered message. If email sending fails, abandon the message in a queue subscription to retry sending email. Benefits. Rapid development. Visual Designer enables quick creation of complex integrations without writing code. Connectivity. Connect Service Bus to hundreds of other services, databases, APIs, SaaS apps with ease. Long-running workflows. Ideal for orchestrating multi-step business processes that might involve human approvals or external system interactions. Event Grid, notifications and event brokerage. Azure Event Grid is a highly scalable, fully managed event routing service. While Service Bus is a message broker for commands and events that require durable storage and transactional capabilities, Event Grid is an event distribution service designed for rapid, reactive event handling. It's often used to notify systems about events rather than to queue messages for processing. How Event Grid integrates with Service Bus. Event Grid can integrate with Service Bus in two key ways. Service Bus as an event source. Event Grid can publish events about your Service Bus entities. Events. Active messages available with no listeners. A signal that messages are queuing up but no one is listening. Dead-letter messages available with no listeners, messages in DLQ without a processor, or queue topic subscription created deleted. Use cases. Trigger an Azure function to scale out consumers if active messages available with no listeners fires. Send an alert via email SMS if dead-letter messages available with no listeners fires, prompting operators to check the DLQ. Audit infrastructure changes when a new queue is created. Service Bus as an event handler. Event Grid can route events from other sources to a Service Bus queue or topic. Use cases. When a blob is created in Azure Storage, Event Grid source, send a message to a Service Bus queue to trigger image processing. When a new resource is deployed in Azure, Event Grid source, send a message to a Service Bus topic for auditing. Example, scaling out consumers with Event Grid. Scenario, too many messages accumulating in a queue with no listeners. Conceptual flow, Service Bus, event source. Event Grid monitors your Service Bus queue for the active messages available with no listeners event. Event Grid, event router, routes this event to an Azure function. Azure function, event handler, triggered by the Event Grid event. This function receives the event data, which includes the queue name. It then checks the current scale settings of your consumer application, e.g., Azure App Service Plan, Azure Container Apps, or Kubernetes deployment. It initiates an auto-scaling action, either by increasing the instance count, adjusting min-max thresholds, or triggering a custom scaling script. Benefits: reactive architectures. Quickly react to changes and events within your Azure ecosystem. Decoupled event flow. Event Grid provides a highly scalable and resilient way to route events without tight coupling between event publishers and subscribers. Simplified monitoring. Event Grid can act as a simple way to get notifications about the crucial state changes in your service bus. General integration patterns. Beyond specific service pairings, here are some broader integration patterns that benefit from Service Bus. Asynchronous API endpoints. A client makes an HTTP POST request to an Azure function or app service. The function immediately sends a message to a Service Bus queue, returns an HTTP 202 accepted response to the client, and delegates the long-running processing to an asynchronous worker that processes messages from the queue. This provides responsive APIs. Cross-service communication. Microservices in different Azure services, e.g., an Azure Kubernetes Service (AKS) application, an Azure Functions app, and an Azure Web App, can communicate reliably using Service Bus without needing direct API calls between them. Bridging on-premises and cloud. Service Bus can be used as a reliable bridge for messages exchanged between on-premises applications, perhaps using Service Bus Relay, a related though distinct service, or hybrid connections, and cloud-based systems. Batch processing coordination. A Service Bus queue can collect small work items, and once a certain number or specific timing is met, an Azure function, using a time trigger or a batch trigger, can process these items as a batch. Conclusion: Azure Service Bus is much more than a standalone message broker. It is a powerful connector that facilitates robust, asynchronous communication across the diverse landscape of Azure services. By understanding how to effectively integrate Service Bus with Azure functions for serverless processing, Logic Apps for low-code workflow orchestration, and Event Grid for reactive event handling, you can design and build highly scalable, resilient, and event-driven distributed systems. These integrations allow you to leverage the strengths of each service, creating solutions that are both powerful and operationally efficient. In the next chapter, we will delve into performance optimization and cost management for your Service Bus solutions. Chapter 10: Performance, Cost, and Scalability. Building a robust messaging system is not just about functionality. It's also about ensuring it performs under load, scales efficiently, and remains cost-effective. Azure Service Bus offers features and configurations that significantly impact its throughput, latency, and operational expense. This chapter dives deep into optimizing your Service Bus solutions for performance and cost, helping you make informed decisions for your production deployments. Factors affecting Service Bus throughput. Throughput in Service Bus refers to the rate at which messages can be sent to and received from your queues and topics. Several factors influence this, and understanding them is key to optimization. Pricing tier. As discussed in Chapter 2, the chosen pricing tier, Standard Vs Premium, is the most significant factor. Standard tier offers shared capacity, meaning throughput can vary and might be affected by noisy neighbors. It has lower guaranteed limits compared to Premium. While suitable for many production workloads, it might experience throttling under heavy, sustained load. Premium tier provides dedicated resources, messaging units, guaranteeing predictable, higher throughput and lower, more consistent latency. This is crucial for high-performance and mission-critical scenarios. Message size. Smaller messages can be processed faster than larger ones. The overhead of network transmission and storage for 1 MB messages is significantly higher than for 1 KB messages. While Service Bus supports messages up to 1 MB, standard, or 100 MB, premium, breaking down large messages into smaller, more granular ones, e.g., sending a pointer to a blob storage for a large file instead of encoding the file directly in the message generally yields better performance. Sending patterns. Batching, sending multiple messages in a single operation, send messages async, is significantly more efficient than sending them one by one. This reduces the number of network round trips and protocol overhead. Asynchronous sends always use asynchronous API calls, e.g., send message async, send messages async. Synchronous calls block the sender, reducing overall throughput. Receiving patterns, prefetching. Service bus clients can prefetch a configurable number of messages into a local buffer. This significantly improves receive performance by reducing the need to wait for Service Bus to send messages at each receive request. It's especially effective in peak clock mode. Concurrency, running multiple message processing tasks concurrently within a single consumer application instance, or scaling out to multiple consumer instances, allows for parallel processing of messages from the same queue subscription. Batch receiving, just like sending, receiving messages in batches, receive messages async, can also improve efficiency, though the benefits are often smaller than sending batches if prefetching is well configured. Network latency. The geographical distance between your application and the service bus namespace naturally affects performance. Choose a region close to your deploying applications. Optimizing message sending. Batching messages. Batching is perhaps the single most impactful optimization for message sending throughput. Conceptual sender batching. Setup, service bus client, service bus sender. var messages to send equals new list service bus message. For int I equals 0, I 100, I++, example. 100 messages. var message body equals test message, plus I. Messages to send add, new service bus message body. Send all messages in a single batch operation. The SDK automatically splits large batches if they exceed service bus message size limits. Await sender send messages async messages to send. Print sent plus messages to send .count plus messages in a single batch. It's common practice to buffer messages on the sender side and send them in batches when the buffer reaches a certain size, e.g., 100 messages, or after a short timeout, e.g., 1 second, whichever comes first. This ensures that messages are sent with minimal latency and high efficiency. Optimizing message receiving. Prefetching. Prefetching can dramatically improve the effective throughput of your receiver applications. Instead of retrieving one message at a time, the client brings a specified number of messages into a local in-memory buffer. When the application requests a message, it's served from this local buffer, reducing the latency typically associated with a network round trip to service bus. Conceptual prefetch configuration. Setup, service bus client. Create a processor with prefetch set. var processor options equals new service bus processor options. Max concurrent calls equals 10. Process up to 10 messages concurrently. Prefetch count equals 20. Prefetch 20 messages into the local buffer. To create a processor for the queue subscription. Processor equals client create processor, queue name, processor options. Register handlers and start processor as before. Choosing a prefetch count. A good starting point for prefetch count is typically 2 to 3 times max concurrent calls. For example, if processing 10 messages concurrently, prefetching 20 to 30 might be effective. Too low a prefetch count might lead to your consumers idling while waiting for messages. Too high a prefetch count can lead to messages sitting in the receiver's local buffer for too long if processing is slow, potentially causing their lock duration to expire and message redelivery, though the SDK often handles lock renewal for prefetched messages. Find a balance that keeps your consumers busy without holding messages unnecessarily. Concurrency. Running multiple concurrent message processing tasks within your consumer application or deploying multiple instances of your consumer application allows for parallel message processing. Max concurrent calls for service bus processor. This setting determines how many concurrent message handlers the processor will invoke. Each max concurrent calls runs on a separate thread, allowing your application to process multiple messages in parallel. Scaling out application instances. For higher scale, deploy multiple instances of your consumer application. Service Bus automatically distributes messages among these competing consumers. Deep dive into Service Bus pricing models and cost optimization. Understanding the pricing model is crucial for managing your Azure costs. Service bus pricing varies significantly between the standard and premium tiers. Standard tier pricing. The standard tier pricing is a bit more complex, based on base charge, a fixed hourly charge for the namespace. Brokered connections. A charge for each brokered connection, each open connection from your application to Service Bus that is active for more than an hour per day. Consolidating connections where possible reduces this cost. Messaging operations. Messages are metered in operations, e.g., send, receive, complete, abandon, dead letter. These are accumulated and then aggregated into blocks. The first set of blocks per month is free, and then you pay per block. Cost factor. Higher message volume means more operations, leading to higher costs. Long lock duration and message redeliveries, due to frequent abandon calls, also contribute to operations. Premium tier pricing. The premium tier offers a simpler, more predictable pricing model based on messaging units, MUs. Messaging units, MUs, you allocate MUs to your namespace. Each MU provides a set amount of dedicated resources, CPU, memory, storage, throughput. You pay a fixed hourly rate per MU allocated, regardless of usage. Benefits: predictable cost, guaranteed performance, no per-operation charges, no brokered connections charges. Cost factor: the number of MUs you provision. You pay for allocated capacity, not usage. Cost optimization strategies. Choose the right tier. Start with standard, for development, testing, and many lower-volume production workloads. Upgrade to premium when needed. If you require sustained, high throughput, predictable latency, dedicated resources, or advanced features like VNet integration, private endpoints, or GeoDoctor, while premium has a higher base cost. It can be more cost-effective for very high volumes due to no per-operation charges, and it offers much better performance guarantees. Migration. You can migrate from standard to premium, but not directly from premium to standard. Optimize message size. Smaller messages are cheaper to send on standard tier due to operation costs and require less bandwidth overall. Consider storing large payloads in Azure Blob Storage and sending only a reference URL in the Service Bus message body. Batching. As discussed, batching messages significantly reduces brokered connections and operations costs in the standard tier, as typically a batch send counts as a single operation. Prefetching and concurrency at receiver. These optimizations reduce the number of individual receive calls and improve the speed at which messages are processed. This helps clear the queue faster and reduces the duration messages are held, which indirectly can affect costs related to message aging, especially if your message TTL is long. Monitor and scale MUs, premium. If using premium, carefully monitor your performance and adjust MUs to match your workload. Avoid over-provisioning MUs during low usage periods as you pay for allocated capacity. You can scale MUs programmatically or via the Azure portal. Review max delivery count. While essential for reliability, a very high max delivery count combined with persistent consumer errors can lead to messages bouncing between the queue and your consumer for an extended period, consuming operations and potentially delaying other messages. Balance reliability with efficient error handling, dead lettering when appropriate. Clean up unused entities. Regularly remove queues, topics, and subscriptions that are no longer in use to avoid unnecessary base charges and resource consumption. Conclusion: optimizing Azure Service Bus for performance and cost is an ongoing process that involves understanding its underlying mechanics and your application's specific needs. By diligently applying batching for sends, prefetching and concurrency for receives, and making informed decisions about your pricing tier and messaging unit allocation, you can achieve both high throughput and cost efficiency. Coupled with careful consideration of message size and robust error handling, these strategies ensure your service bus deployment is not just functional, but also performant and economical. In the next chapter, we will shift our focus to common scenarios and design patterns, showing you how to apply Service Bus effectively to solve real-world architectural challenges and build sophisticated distributed systems. Chapter 11: Common Scenarios and Design Patterns. Azure Service Bus, with its rich feature set, is a powerful tool for solving a wide array of distributed system challenges. This chapter will explore common architectural patterns and real-world scenarios where Service Bus plays a pivotal role. We'll delve into how you can leverage its capabilities to build robust, scalable, and maintainable microservices, orchestrate complex business processes, and achieve eventual consistency across your systems. 11.1 Competing Consumers Pattern. Scaling out message processing. The competing consumers pattern is a fundamental pattern for message processing scalability. It addresses the need to process messages from a single queue concurrently and efficiently. The pattern concept: multiple independent consumer instances, workers, are deployed to read and process messages from the same queue. Each message is processed by only one consumer instance. How Service Bus enables it: shared queue. All consumer instances listen to the same Azure Service Bus queue or a topic subscription. Message locking, peak lock. When a consumer picks a message, Service Bus places a lock on it, peak lock mode. This prevents other consumers from picking up and processing the same message concurrently. Automatic distribution. Service Bus automatically distributes incoming messages among the available and active consumer instances. Benefits: scalability. As message volume increases, you simply add more consumer instances to scale horizontally. Reliability. If one consumer instance fails, other instances can continue processing messages from the queue. Uncompleted messages, due to failure, become available for other instances after the lock expires. Load balancing. Service Bus naturally acts as a load balancer, distributing messages evenly across active consumers. Efficiency maximizes resource utilization by keeping available consumer instances busy. Use case: image processing service. Imagine a system that processes user-uploaded images, e.g., resizing, watermarking. User uploads image. When a user uploads an image to blob storage, a simple event or a record in a database is created. Message generation. A service, e.g., an Azure function triggered by the blob upload event, places a message onto an image processing queue on Service Bus. The message contains information about the image location and required operations. Competing consumers. Several instances of an image processor microservice, e.g., deployed as Azure functions, app services, or in AKS, are listening to the image processing queue. Processing. Each available image processor picks up a message, processes the image, and then completes the message. If an instance fails, the message returns to the queue and another instance will pick it up. This pattern allows the image processing workload to scale dynamically with demand, ensuring images are processed quickly without overwhelming any single worker. 11.2 Request reply pattern. Building synchronous-like interactions. While the core strength of messaging is asynchronous communication, there are often scenarios where an application needs to send a message and then wait for a specific response from the recipient, simulating a synchronous call. The request reply pattern facilitates this. The pattern concept: a sender sends a request message and expects a specific reply message within a certain timeframe. How Service Bus enables it: sender, requester, sends a request message to a request queue or topic, sets the reply to property of the message to a unique address, e.g., a temporary or dedicated reply queue specific to this requester instance, sets the correlationid property to a unique identifier for this specific request, waits for a reply message on its reply to queue, filtering by the correlationid. Receiver, replier, listens to the request queue, processes the request message, sends a reply message back to the address specified in the reply to property of the original request. Crucially, sets the correlationid of the reply message to match that of the original request. Benefits: decoupling. Unlike direct HTTP calls, the requester and replier remain decoupled. They don't need direct network access to each other. The broker facilitates the communication. Resilience. Messages are persisted by Service Bus, so if the replier is temporarily down, the request waits. If the requester crashes, it can potentially resume waiting for replies, though managing state here can be complex. Load balancing. Multiple repliers can process requests from the request queue using the competing consumers pattern. Use case: credit check service. An e-commerce order system needs to perform a credit check. It does not want to block the user during this potentially long-running external process, but does need the result to proceed. Order service requester publishes a credit check request message to a credit check request queue, sets reply to credit check replies queue, sets correlation id to the order id, temporarily waits on credit check replies for a message with the matching correlation id. Credit check service replier listens to credit check request queue, picks up a message, calls an external credit agency API, which might take time, receives the credit score, publishes a credit check reply message to the credit check replies queue, sets correlation id to the original order id. Order service requester receives the credit check reply from its credit check replies queue, continues processing the order based on the reply, e.g., approve or reject order. It's common for the requester to set a timeout for the reply. If no reply is received within that time, it can assume failure or trigger alternative processing. 11.3 Saga Pattern Managing Distributed Transactions. In a microservices architecture, a single business operation might span multiple services, each with its own database. For example, processing an e-commerce order might involve order service creates order, inventory service reserves stock, payment service charges customer, shipping service arranges delivery. If the payment fails, all preceding services that performed actions must be compensated, e.g., order canceled, stock released. This is the challenge of distributed transactions, and the Saga pattern is a common solution. The pattern concept. A saga is a sequence of local transactions, where each transaction updates its own database and publishes an event that triggers the next step in the saga. If a step fails, the saga executes a series of compensating transactions in reverse order to undo the previously completed steps. How Service Bus enables it. Service Bus topics and queues is the communication backbone for SAGOs. Events. Services publish events to Service Bus topics when their local transactions complete. Commands. Saga orchestrators, or participant services, send commands to Service Bus queues to trigger actions in other services. Reliability. Service Bus ensures reliable delivery of events and commands, crucial for the saga's coordination. Two main types of SAGOs. Choreography-based saga. Each service produces events and other services react to those events. There's no central orchestrator. Each service listens for specific events and publishes new events upon completion of its local transaction. While simpler to implement for small SAGOs, it can become hard to reason about and debug as complexity grows. Orchestration-based saga. A dedicated orchestrator service manages the entire workflow. It sends commands to participant services, waits for their responses, events, and decides the next step or which compensating transactions to execute. This is often preferred for more complex SAGOs as it centralizes the logic. Use case: e-commerce order fulfillment. Using an orchestration-based saga for order fulfillment, order service receives a new order, creates the order in its DB local transaction, publishes order created event to Service Bus order events topic. Saga orchestrator, e.g., Azure Function Logic App, subscribes to order events topic on order created event, sends reserve stock command to inventory service queue, listens for stock reserved event or stock reservation failed event from inventory service topic. If stock reserved event, sends charge customer command to payment service queue. If stock reservation failed event, sends cancel order command to order service queue, compensating transaction, and then marks saga as failed. Listens for customer charged event or charge failed event from payment service topic. If customer charged event, sends arrange delivery command to shipping service queue. If charge failed event, sends release stock command to inventory service queue and cancel order command to order service queue, compensating transactions, then marks saga as failed. And so on, coordinating each step and defining compensating actions for every failure point. While complex, the saga pattern using Service Bus ensures eventual consistency in distributed systems, minimizing the risk of data inconsistencies across disparate services. 11.4 Command Vs. Event messaging. Understanding the distinction between commands and events is crucial for designing clean, effective message-driven architectures. Commands: intent, an instruction to do something. Nature: imperative. Do this. Target, usually a specific recipient or a single logical service that is responsible for performing the action. Example, create order command, charge customer command, ship product command. Best practice, usually sent to queues because they typically have a single, well-defined handler. Events, intent, a notification that something has happened. Nature, declarative. This happened. Target, unaware of specific recipients. Multiple services might be interested. Example, order created event, product shipped event, payment failed event. Best practice, usually published to topics, using the publish-subscribe pattern because multiple consumers might subscribe to react to something that occurred. Choosing between a command and an event influences the messaging pattern you choose and how your services are designed to interact. 11.5 Practical Architectures for Microservices Communication. Service Bus often serves as the asynchronous communication layer for microservices. Point-to-point, queue-based. Microservice A sends an processing job command to microservice B's dedicated queue. Microservice B picks up from its queue. Suitable for direct requests between two services, managing tasks like send email. Event-driven, topic-based. Microservice A publishes entity-created event to a shared domain events topic. Microservice B and C, interested in this event, subscribe to domain events and filter for entity-created event. Suitable for broadcasting changes, reacting to business events, e.g., customer updated, inventory adjustment. Request reply, queues. Microservice A sends query data request to microservice B's request queue, expecting a reply on its reply queue. Suitable for synchronous-like communication for specific queries where immediate feedback is needed. Hybrid, queues, and topics. Many microservice architectures use a blend. Commands go to queues, domain events go to topics. Example, a typical e-commerce microservice setup with Service Bus. Order service receives create order command from order queue. Publishes order created event to order events topic. Publishes order canceled event to order events topic. Payment service receives charge customer command from payment queue. Publishes payment charged event to payment events topic. Publishes payment failed event to payment events topic. Inventory service receives reserve stock command from inventory queue. Publishes stock reserved event to inventory events topic. Publishes stock released event to inventory events topic. Notification service subscribes to order events topic for order created event, order canceled event. Subscribes to payment events topic for payment charged event, payment failed event. Sends email SMS notifications based on these events. This highly decoupled architecture allows each service to operate, scale, and evolve independently, with Service Bus acting as the resilient, central communication fabric. Conclusion: Azure Service Bus is a versatile tool that enables the implementation of complex and resilient messaging patterns. By understanding how to apply the competing consumers pattern for scalable processing, the request reply pattern for synchronous-like interactions, and the saga pattern for distributed transactions, you can tackle some of the most challenging problems in distributed system design, differentiating between commands and events, and seeing how they integrate into microservices communication provides a strong foundation for building robust, event-driven architectures. In our final chapter, we'll discuss some advanced topics and contemplate the road ahead for messaging in the cloud. Chapter 12. Advanced Topics and the Road Ahead. Throughout this book, we've journeyed from the fundamentals of asynchronous messaging to the intricate details of Azure Service Bus, exploring its advanced features, security, operational best practices, and integration patterns. You are now equipped with the knowledge to design and implement robust, scalable, and reliable message-driven applications in Azure. In this final chapter, we'll briefly delve into some advanced distinctions, touch upon enterprise integration patterns, and consider the exciting future of messaging paradigms. Distinguishing Service Bus from Kafka/Event Hubs, a deeper dive. While we touched upon the differences between Service Bus, Event Hubs, and Event Grid in Chapter 1, it's worth revisiting the distinction between Service Bus and stream-based platforms like Event Hubs or Apache Kafka, when considering their core use cases and architectural fit. Feature Azure Service Bus, Queues Topics, Azure Event Hubs, or Apache Kafka. Yeah. Primary purpose message broker. High-value message queuing for commanding and eventing, reliable delivery, transactional. Event stream platform. High throughput, low latency event ingestion and stream processing. Message persistence messages are typically transient. Once consumed and completed, they are removed. Events are persisted for a configurable retention period, e.g., 1 to 7 days in append-only logs. Consumption semantics point-to-point, queue, publish-subscribe topic. Messages are owned and removed by consumers. Event streaming replay. Multiple consumers can read the same event stream independently. Delivery guarantee optimized for at least once delivery, sometimes exactly once processing with idempotency. At least once delivery per consumer group. Message order guaranteed order within a session. Best effort elsewhere. Guaranteed order within a partition. Features transactions, sessions, message deferral, scheduled messages, duplicate detection, rich filtering rules. Consumer groups, offset management, stream replay, large number of concurrent readers. Typical messages, commands, e.g., process this order, discrete events, e.g., order paid. Records of fax events, e.g., sensor reading X at time T, user clicked Y. Scalability, throughput limited by namespace/entity capacity, muse, partitions. Highly scalable for ingestion, scales linearly with partitions. When to choose, Azure Service Bus. Use when you need reliable, durable queuing for messages that serve as commands or critical business events, requiring guaranteed delivery and transactional integrity. Scenarios include long-running workflows, messages that drive state changes, or when strict ordering session is required for a logical group of messages. It's excellent for connecting applications that need to communicate reliably with each other. Azure Event Hubs or Kafka. Use when you have very high volumes of events, typically immutable facts, that need to be ingested rapidly and processed by multiple, independent consumers. This is ideal for telemetry, IoT data, log aggregation, real-time analytics, and event sourcing where you might want to replay historical events. The core idea is stream processing, not message processing. Often, Service Bus and Event Hubs are used together. For example, Event Hubs might ingest raw telemetry data from IoT devices, and after some initial stream processing, a command to take action, e.g., open valve X, might be sent to a service bus queue for reliable delivery to an actuator. Enterprise integration patterns and Service Bus. The comprehensive capabilities of Azure Service Bus allow it to implement many of the classic enterprise integration patterns, EIPs, described by Gregor Hope and Bobby Wolf. These patterns provide a common language and solution framework for connecting enterprise applications. Service buses features directly support EIPs such as message channel, queues, and topics. Message, Service Bus message with properties. Message router, topic subscriptions with rules, filters. Pipes and filters, chains of consumers where each processes a message and sends it to the next queue. Message broker/event-driven consumer. The entire Service Bus architecture and how applications consume from it. Dead letter channel, the dead letter queue. Idempotent receiver, achieved through duplicate detection and careful consumer design. Request reply, implemented with reply to and correlationed. Publish subscribe, implemented with topics and subscriptions. Guaranteed delivery, achieved through P-clock and message persistence. Understanding EIPs provides a valuable framework for designing sophisticated message-driven solutions, and Azure Service Bus provides the ready-made components to implement them effectively. Hybrid cloud messaging considerations. As organizations increasingly adopt hybrid cloud strategies, combining on-premises infrastructure with cloud services, Service Bus continues to play a vital role in bridging environments. Azure Relay. A Service Bus-related service, Azure Relay, enables exposing services running in your corporate network securely to the public cloud without opening firewall ports or deploying VPNs. Messages passed through Relay can then interface with other Azure services, including Service Bus. Hybrid connections, Azure App Service/Azure Functions. Allow your Azure PaaS applications to securely access resources in a corporate network, e.g., a database or message queue, without requiring full VPN access. VPNs/ExpressRoute. For more robust and dedicated connectivity, traditional VPNs, site-to-site, or Azure ExpressRoute can securely extend your on-premises network into Azure, allowing seamless communication with Service Bus as if it were on your local network. These technologies enable you to seamlessly integrate legacy, on-premises applications with modern cloud-native components, orchestrating workflows that span environments. The road ahead. Future trends in messaging. The landscape of cloud messaging is constantly evolving. Here are a few trends and considerations to keep an eye on. Serverless first. The tight integration of Service Bus with Azure Functions, Logic apps, and container apps will continue to deepen, making it even easier to build event-driven, scale-to-zero architectures without managing servers. Event-driven architectures, EDA maturity. As organizations adopt EDAs more widely, the patterns and best practices for managing state, distributed transactions, sagas, and observability in highly distributed systems will become more refined. Service Bus positions you well for this. Real-time data streams. The convergence of traditional message queuing with real-time stream processing will continue. As discussed, knowing when to use Service Bus versus Event Hubs versus streaming analytics will remain critical. AI/ML integration. Messaging systems will increasingly serve as the ingestion and distribution layer for AI and machine learning pipelines, feeding data to training models and distributing inference results to consuming applications. Observability. Enhanced tools and practices for tracing messages end-to-end across a distributed system, e.g., distributed tracing standards, will become more crucial for debugging messages flowing through Service Bus and other brokers. Quantum computing and messaging. While still nascent, the potential long-term influence of quantum computing on cryptography and secure communication mechanisms could eventually lead to new requirements for messaging systems. Summary and next steps. Throughout this book, Azure Service Bus Unveiled, we've covered a vast range of topics, from its core concepts to advanced patterns and operational considerations. You should now understand the why of asynchronous messaging. Be confident in setting up and managing Azure Service Bus namespaces, queues, topics, and subscriptions. Know how to send and reliably receive messages, including using pclock and handling message settlement. Be able to leverage advanced features like dead letter queues, scheduled messages, message deferral, duplicate detection, and message sessions. Grasp the principles of transactional messaging and designing idempotent consumers for reliable processing. Know how to secure your Service Bus resources using AAD RBAC and network isolation. Understand how to monitor, manage, and optimize your Service Bus for performance and cost. Be familiar with common messaging patterns like competing consumers, request reply, and SAGOs, and their application in microservices. Appreciate the role of Service Bus in the broader Azure ecosystem, especially with Azure Functions, Logic apps, and Event Grid. Your journey continues. The world of distributed systems is vast and constantly evolving. As you apply the knowledge gained from this book, consider these next steps. Practice. The best way to solidify your understanding is to build. Experiment with the features and patterns discussed. Try implementing some of the conceptual code from the book in your preferred language. Explore official documentation. Azure documentation is extensive and constantly updated. Refer to it for the latest API details, best practices, and troubleshooting guides. Engage with the community. Join Azure developer communities, attend webinars, and read blogs. Learning from others' experiences is invaluable. Stay updated. Follow Azure announcements and updates. New features and improvements are released regularly. Azure Service Bus is a powerful and indispensable component for building robust cloud-native applications. By mastering its capabilities, you are well-positioned to tackle complex enterprise integration challenges and build highly scalable, resilient, and responsive distributed systems that can adapt and thrive in the ever-changing cloud landscape. Thank you for embarking on this journey with me. May your messages flow reliably and your systems always be in sync.